Hello there and welcome back to the Science Sleepy Minds. Tonight, you're standing at the very edge of everything. Not the edge of your bed, not the edge of your neighborhood, but the actual bleeding rim of observable space where light itself gives up and turns around. Somewhere out there, right now, as you settle into your pillow and pull the blanket a little closer, there are objects so dense, so violently hungry, that they swallow entire stars the way you might swallow a midnight snack. They bend time. They crush matter into dimensions you cannot picture. They are black holes, and tonight we're going to meet the most terrifying ones ever discovered. You probably will not survive this journey, not physically anyway, but your mind is going to take one spectacular ride. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Also, drop a comment telling me where you are listening from and what time it is where you are. I always love reading those. Someone is always tuning in at 3 a.m. from somewhere beautifully random. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You feel the hum first, a low vibration in your chest, as though the universe itself is breathing against your ribs. You're floating now, weightless, wrapped in the velvet nothing of deep space. Stars pepper every direction, tiny and cold and impossibly far apart, and for a moment the scene is almost peaceful. Almost. Because directly ahead of you, something is wrong with the sky. There is a patch where the stars are not just absent but actively disappearing, like someone is taking an eraser to a chalkboard full of glitter. The darkness there is not empty. It is full. It is so full of mass that it has punched a hole in the fabric of reality and everything nearby. Light, dust, unlucky comets is spiraling into it like water circling a drain in slow, elegant horror. You have just laid eyes on a black hole, and even from this safe imaginary distance, some primal corner of your brain is screaming at you to leave. But you will not leave, because curiosity is a beautiful curse, and tonight we are leaning all the way into it. Black holes are, without exaggeration, the most extreme objects the universe has ever produced. They are born from violence sustained by gravity, and decorated with physics so strange that even the scientists who study them occasionally throw their hands up and mutter something unprintable. Albert Einstein's general theory of relativity, published back in 1915, predicted that space-time could curve so dramatically around a sufficiently dense mass that nothing, not even light travelling at 300,000 kilometers per second, could climb back out. Einstein himself was reportedly a little uncomfortable with the implication. He thought nature would find some way to prevent such an absurd object from forming. Nature, as it turns out, did not get that memo. The term black hole was not even coined until 1967, when physicist John Archibald Wheeler popularized it during a lecture. Before that, scientists used the far less catchy phrase gravitationally completely collapsed object, which, you have to admit, does not exactly roll off the tongue at a dinner party. Wheeler's two-word label stuck because it was vivid and terrifying and accurate, 3 qualities that rarely show up in the same physics term, and here is a quirky little footnote that most textbooks skip. Wheeler almost did not use the phrase at all. He later claimed that an anonymous audience member shouted it out during his talk and he simply adopted it. Scholars still argue whether that story is true or whether Wheeler was just being modest, but either way, the name changed everything. Suddenly, the public had a label for the monster under the cosmic bed, and imaginations ran wild. You drift a little closer to that dark smudge ahead of you and notice something eerie. The stars behind it are not simply vanishing, they are bending. Their light is curving around the black hole's gravitational field, creating a shimmering halo, a ring of warped starlight that physicists call an Einstein ring. It is gorgeous in the way a riptide is gorgeous, beautiful right up until the moment it kills you. This effect, gravitational lensing, was one of the first confirmations that Einstein's equations were more than just elegant math. In 1919, astronomer Arthur Eddington measured the bending of starlight during a solar eclipse and found it matched general relativity's predictions almost perfectly. The sun, of course, is a featherweight compared to a black hole, but the principle is the same. Mass tells space-time how to curve, and space-time tells light how to travel. And when there is enough mass in a small enough volume, the curve becomes a trap. Now imagine condensing our entire sun, all 1.99 octillion kilograms of it, into a sphere roughly 6 kilometers across. That is about the size of a modest city, maybe Manhattan if you squish the buildings together. At that density, the escape velocity at the surface would exceed the speed of a light, and you would have yourself a black hole. The boundary where escape becomes impossible is called the event horizon, and it is not a physical wall. You would not bump into it. You would not hear a click or see a velvet rope. You would simply cross an invisible line in space-time, and from that instant every possible path you could travel, forward, backward, sideways, would lead deeper in. The future itself would point toward the center. That is not a metaphor. In the math of general relativity, once you cross the event horizon, the singularity is not a place in space. It is a moment in your future, as unavoidable as next Tuesday. And this is just the beginning. What you're staring at right now is a modest stellar mass black hole, maybe 10 or 15 times the mass of our sun. It is terrifying, sure, but on the grand roster of cosmic nightmares, it barely registers. Out there, hiding in the hearts of galaxies and lurking in the voids between stars, are black holes millions, billions, even tens of billions of times heavier. Some spin so fast they drag the very fabric of space-time around them like a toddler dragging a blanket. Some fire jets of superheated plasma across distances longer than our entire galaxy is wide. Some should not even exist according to our best models, and yet there they sit, embarrassing our equations. Over the coming minutes, you and I are going to visit them one by one, from the first black hole humanity ever confirmed to monsters so massive they make our sun look like a grain of sand on an infinite beach. You will learn how they are born, how they feed, how they warp time, and how, in the impossibly distant future, they will be the last objects standing in a universe gone cold and dark. So settle in, let your breathing slow, feel the imaginary starlight on your face and the impossible silence of the vacuum around you. We are heading deeper now, toward the death of a massive star, because every black hole begins with an ending, and the story of that ending is as dramatic as anything the cosmos has ever staged. You turn your gaze away from that dark smudge on the horizon, and let the stars carry your attention to something brighter, something still alive. There, blazing against the blackness like a lantern left on a porch, is a massive star. Not a modest thing like our sun, which is frankly a bit of a lightweight in the stellar lineup, but a true giant, perhaps 20 or 30 times the sun's mass, burning through its nuclear fuel with the reckless enthusiasm of someone who knows they're not going to be around long. This star is blue-white, searingly hot, and it has maybe a few million years left on its clock. That sounds like a lot until you remember our sun has been chugging along for nearly 5 billion years and still has roughly 5 billion more to go. Massive stars live fast, burn bright, and die in the most spectacularly violent fashion the universe permits. You're about to witness that death, and from it, a black hole will be born. The process starts in the core. For most of a massive star's life, it survives by fusing hydrogen into helium, the same reaction that powers our sun, just cranked up to absurd intensity. The outward pressure from this fusion is the only thing keeping the star from collapsing under its own gravity. Think of it as a cosmic arm wrestling match. Gravity pulls inward, radiation pushes outward, and for millions of years the two forces hold each other in a tense, shimmering stalemate. But fusion is not free. It requires fuel, and fuel runs out. When the hydrogen in the core is exhausted, the star does not simply go dark. Instead, the core contracts, heats up, and begins fusing helium into carbon. When the helium runs out, carbon fuses into neon, then neon into oxygen, then oxygen into silicon. Each new fuel ignites at a higher temperature and burns for a shorter period. The silicon burning phase, the very last act, lasts roughly 1 day. One single day after millions of years of life. There is something almost poetic about that, like a novel that spends 400 pages building to a final chapter you can read during your lunch break. And here is where things go catastrophically wrong. When silicon fuses, it produces iron. Iron is the end of the line. Fusing iron does not release energy, it absorbs it, which means the core suddenly loses the very thing that was holding the star up. It is as if someone pulled the legs out from under a table stacked with bricks. The core collapses at roughly 1/4 of the speed of light, which is so fast that if you blinked at the moment it started, you would miss the entire implosion. In less than a second, a core the size of Earth is crushed into a ball perhaps 20 kilometers across. The density becomes so extreme that protons and electrons are smashed together into neutrons, and for a brief, astonishing moment, the infalling material bounces off this neutron core like a rubber ball hitting a wall. That bounce sends a shockwave roaring outward through the rest of the star, and what follows is a supernova, one of the most energetic events in the known universe. During the peak of a core collapse supernova, the dying star can briefly outshine its entire host galaxy. Billions of stars, and this one, in its death throes, produces more light than all of them combined. The explosion scatters heavy elements, gold, platinum, uranium, everything forged in the star's layered furnace, across light years of space. Those elements will eventually seed new stars, new planets, and in at least one case we know of, new life. The calcium in your bones and the iron in your blood were manufactured inside a star that died before our solar system even existed. You are, in a very literal sense, a monument to stellar death. That thought is either deeply comforting or mildly unsettling, depending on your mood at 3 a.m. Now, for many massive stars, the supernova is the end of the drama. The core left behind stabilizes as a neutron star, an object so dense that a teaspoon of it would weigh about 6 billion tons, which is roughly the combined weight of every human being on Earth crammed into a space smaller than a sugar cube. Neutron stars are wild enough on their own, spinning hundreds of times per second, generating magnetic fields 1 trillion times stronger than Earth's, occasionally shooting beams of radiation across the galaxy like cosmic lighthouses. But they are not black holes, they stop just short of the edge. For a neutron star to form instead of a black hole, the original star generally needs to be below a certain mass threshold, somewhere around 20 to 25 solar masses, though the exact number is still a matter of lively academic debate. Astrophysicists argue about this boundary the way neighbours argue about fence lines, politely at first and then with increasing intensity at conferences. If the original star is massive enough though, nothing stops the collapse. The neutron core cannot hold. There is no known force in physics strong enough to resist gravity at this scale. The matter keeps falling inward, crushing past the neutron star stage, past any conceivable state of matter, until it is compressed into a point of theoretically infinite density called a singularity. Around that singularity, space-time warps so severely that the event horizon forms, that invisible boundary from which not even light escapes. And just like that, the universe has a new black hole. The whole process, from iron catastrophe to singularity, takes less than a second. In the time it took you to read this sentence, a star somewhere in the observable universe may have just completed this exact journey. Here is a fringe detail that keeps some theorists up at night. There's a class of supernovae called pair instability supernovae, which occur in extremely massive stars, perhaps 150 solar masses or more. In these events, the core gets so hot that photons spontaneously convert into pairs of matter and antimatter particles. This conversion robs the core of radiation pressure so suddenly that the entire star can obliterate itself in a single blast, leaving nothing behind. No neutron star, no black hole, just an expanding cloud of debris and the faint cosmic echo of something that used to be magnificent. The existence of pair instability supernovae creates a theoretical gap in black hole masses, a range where black holes should not form, and yet some discoveries, as we will see a bit later, seem to sit right in that forbidden zone, grinning at our models like a cat on a keyboard. You watch the supernova light fade, and where that massive star once roared, there is now only a small, dark absence. A fresh black hole, still ringing with gravitational vibrations, still settling into its new shape. It does not glow, it does not roar, it simply exists, warping the starlight behind it into a faint, eerie halo. And you realise, floating there in the silence, that this is only the first kind, the small kind, the kind born from a single star's death. Out there, in the hearts of galaxies, in the cradles of the early universe, there are black holes so much larger and so much stranger that this little stellar corpse would be lost in their shadow like a pebble at the foot of a mountain. You're going to meet them, but first you need to understand what happens when you actually fall in, because the journey toward the event horizon is where the terror truly begins. You let yourself drift closer, not because it is wise, not because any reasonable part of your brain thinks this is a good idea, but because the black hole ahead of you has a pull that goes beyond gravity. It is curiosity, that ancient human affliction, the same impulse that made your ancestors poke strange mushrooms and sail toward the edge of the maps. The stellar mass black hole you've been watching sits quietly in the void, bending starlight around its edges like a dark jewel set against velvet, and you want to know what it feels like to approach. So you do. You nudge yourself forward, and the universe begins to change around you in ways that are subtle at first, and then horrifyingly not. The first thing you notice is the light. Stars behind the black hole are not just warped anymore, they are smeared, dragged into elongated arcs that wrap around the dark centre like luminous ribbons. The closer you get, the more the sky distorts, until the entire universe behind the black hole appears compressed into a bright shimmering ring. Everything in front of you is darkness. Everything behind you is a carnival of bent photons. It is beautiful and nauseating in equal measure, like a funhouse mirror designed by someone with a PhD in general relativity and a questionable sense of humour. This is gravitational lensing taken to its extreme, and it means you are now close enough that space-time itself is noticeably curved. Your instruments, if you had any, would be screaming. Now here is where the real nightmare begins, and it has a name that sounds like it belongs on an Italian restaurant menu: spaghettification. The term was actually coined by Stephen Hawking, which tells you something about the man's ability to make terrifying physics sound almost whimsical. The concept is straightforward in principle but ghastly in practice. Gravity weakens with distance. Your feet, being closer to the black hole than your head, experience a stronger gravitational pull. The difference between the force on your feet and the force on your head is called a tidal force, and near a stellar mass black hole, that difference becomes staggering. Your body would be stretched lengthwise and compressed widthwise, pulled into a long, thin strand of matter like a piece of cosmic taffy. You would not be gently elongated. You would be ripped apart at the molecular level, your atoms drawn into a thin filament spiraling toward the singularity. It is, by virtually every measure, the least pleasant way to go. The exact point at which spaghettification becomes lethal depends on the mass of the black hole, and this is one of those counterintuitive details that makes astrophysics feel like it was designed to confuse you on purpose. A smaller black hole, say 10 solar masses, has a relatively tight event horizon, and the tidal forces near it are extreme. You would be shredded well before you reach the event horizon. But a supermassive black hole, one with billions of solar masses, has an event horizon so enormous that the tidal gradient near it is gentle. You could, in theory, cross the event horizon of a sufficiently large black hole and not feel a thing. No stretching, no tearing, no dramatic violin music. You would simply pass through an invisible boundary and only realize your mistake when you notice that every direction you could possibly travel now pointed inward. The exit would not just be locked, it would have ceased to exist. Scholars still debate exactly what a conscious observer would experience in those final moments, whether there would be a flash of compressed starlight, a sense of acceleration, or simply nothing at all. And this brings us to the event horizon itself, that famous point of no return. You hear the phrase tossed around casually, but the reality is stranger than most people imagine. The event horizon is not a surface. You cannot touch it, stand on it, or knock on it. It is a mathematical boundary defined by the Schwarzschild radius, named after Karl Schwarzschild, the German physicist who found the first exact solution to Einstein's field equations in 1916 while, remarkably, serving on the Eastern Front of World War I. Schwarzschild was literally calculating the geometry of black holes in the trenches, which is either the most impressive display of focus in scientific history or the most extreme form of procrastination ever documented. He sent his solution to Einstein in a letter, and Einstein reportedly was astonished that an exact answer even existed. Tragically, Schwarzschild died just months later from an autoimmune disease contracted during his military service. He never lived to see his equations confirmed, never knew that the objects he described would become the most studied mysteries in modern physics. The Schwarzschild radius defines the size of the event horizon for a non-rotating, uncharged black hole. For a black hole with the mass of our Sun, that radius is about 3 kilometers. For a black hole with 10 solar masses, it is 30 kilometers. The relationship is perfectly linear, which is oddly satisfying in a field where almost nothing else is simple. But most real black holes are not the clean, non-rotating type that Schwarzschild described. Most of them spin, some at ridiculous speeds, and spinning black holes are described by a different and far more complicated solution called the Kerr metric, worked out by New Zealand mathematician Roy Kerr in 1963. The Kerr solution introduces a region outside the event horizon called the ergosphere, a zone where space-time itself is dragged around by the black hole's rotation so forcefully that nothing, not even light, can remain stationary. You would be swept along like a leaf in a whirlpool, forced to co-rotate with the black hole whether you wanted to or not. Interestingly, the ergosphere is also the one place where you could theoretically steal energy from a black hole through a process called the Penrose mechanism, proposed by physicist Roger Penrose in 1971. You toss an object into the ergosphere in just the right way, and part of it falls in while the rest is flung out with more energy than it had going in. The black hole loses a tiny bit of its rotational energy, and you walk away, or float away, with a net gain. It is the universe's most dangerous vending machine. Here is a thought that might keep you up tonight, or, given the purpose of this video, gently lull you into a disturbed sleep. From the perspective of an outside observer watching you fall into a black hole, you would never actually cross the event horizon. Time dilation, another gift from general relativity, means that as you approach the horizon, your clock appears to slow down relative to the distant observer. They would see you inch closer and closer, your image growing redder and dimmer as the photons bouncing off your body lose energy climbing out of the gravitational well until you become a frozen, fading ghost, hovering at the edge for what appears to be eternity. You would never vanish. You would just fade, like an old photograph left in the sun. From your own perspective, however, you sail right through without ceremony, and the universe outside the horizon appears to speed up around you, a fast-forwarding blur of cosmic time that you can never rejoin. Two realities, both mathematically valid, both impossible to reconcile with common sense. This is the event horizon, and it is just the doorway. What waits on the other side at the singularity is a question that physics has not yet answered and may never answer, at least not with the tools we have now. You pause here, hovering at a safe distance, and you feel the faintest tug at your feet, a whisper of tidal force reminding you that the abyss is patient. It has nowhere to be. It will wait. And so will we, because there is a specific black hole with a name and a history that changed everything humanity thought it knew about the cosmos, and it is calling to us from the constellation of the Swan. You pull yourself back from the edge, letting the tidal whisper fade from your feet, and you turn toward a familiar patch of sky. The constellation Cygnus, the Swan, stretches its wings across the northern heavens, a graceful cross of stars that ancient Greeks associated with Zeus in disguise, because apparently Zeus could not go anywhere without a costume change. Among those stars, tucked into an unremarkable corner that you would never glance at twice through a backyard telescope, is an object that rewrote the rules of astrophysics. It does not look like much. A faint blue supergiant star called HDE 226868, about 30 times the mass of our Sun, blazing away in what appears to be perfectly ordinary stellar fashion. But something is wrong with it. Something is eating it alive. And in 1964, a pair of Geiger counters strapped to a sounding rocket detected the X-ray screams of its torment. The source was catalogued as Cygnus X1, and it would become the first black hole humanity ever confirmed. You drift closer, and the scene becomes unsettling. The blue supergiant is not alone. It is locked in a tight orbital embrace with something invisible, something roughly 21 times the mass of our Sun that produces no light of its own. Gas is being stripped from the supergiant's outer layers, pulled away in a long spiralling stream that wraps around the unseen companion like thread around a spindle. As this gas falls inward, it forms a swirling disk of superheated material called an accretion disk, and the friction within that disk heats the gas to millions of degrees. At those temperatures, the material radiates furiously in X-rays, and it was those X-rays, sharp and flickering and unmistakable, that the 1964 rocket detected. The source was too compact to be a normal star, too massive to be a white dwarf, and too energetic to be anything astronomers had a comfortable explanation for. Something very dense and very dark was lurking next to that blue supergiant, and it was feeding. The identification of Cygnus X1 as a probable black hole did not happen overnight. It took nearly a decade of observations, arguments, and increasingly sophisticated measurements before the scientific community began to accept what the data was suggesting. The mass of the invisible companion was the key. Neutron stars, the other possible candidate for a compact X-ray source, have a theoretical maximum mass called the Tolman-Oppenheimer-Volkoff limit, which sits somewhere around 2 to 3 solar masses depending on which equation of state you prefer. and physicists have preferences about equations of state the way some people have preferences about pizza toppings, strongly and vocally. Cygnus X1's dark companion blew past that limit with room to spare. It was simply too heavy to be a neutron star. The only remaining option consistent with general relativity was a black hole, and slowly, reluctantly, the astronomical establishment began to nod. But the most famous part of Cygnus X1's story is not the science, it is the bet. In 1974, Stephen Hawking wagered Kip Thorne that Cygnus X1 was not actually a black hole. The stakes were a magazine subscription, a one-year delivery of the satirical British magazine Private Eye from Hawking to Thorne if it turned out to be a black hole, versus a 4-year subscription to Penthouse magazine from Thorne to Hawking if it did not. Hawking later described the bet as an insurance policy. He had spent years working on black hole theory, and if black holes turned out not to exist, at least he would win a magazine. It was the kind of cheerfully fatalistic humour that made Hawking beloved far beyond physics departments. In 1990, as the evidence became overwhelming, Hawking conceded the bet. He reportedly broke into Thorne's office while Thorne was away, found the frame bet on the wall, and signed the concession. Thorne got his magazine. The universe got its first confirmed black hole. Everyone went home mostly happy except perhaps for Thorne's wife, who was reportedly less than thrilled about the Penthouse subscription, though historians still argue whether that detail is embellished. What made Cygnus X1 particularly compelling was not just its mass, but its behaviour. The X-ray emissions flickered on timescales of milliseconds, which told astronomers that the emitting region was extraordinarily small. Light can only travel so far in a millisecond, about 300 kilometers, which meant the X-ray source had to be compact enough to fit within that distance. A 300-kilometer region producing the energy output of thousands of suns is not something you can explain with normal stellar physics. It requires matter being compressed and heated under conditions that only exist near the event horizon of a black hole, where gravitational potential energy is converted into radiation with an efficiency that makes nuclear fusion look lazy. Fusion converts roughly 0.7% of mass into energy. Accretion onto a black hole can convert up to 40%. If our sun ran on black hole accretion instead of fusion, it could produce the same luminosity while consuming a mass equivalent to roughly a dozen grains of sand per second. That is efficiency that would make any engineer weep with joy. Here is a fringe detail that adds a layer of strangeness to the Cygnus X1 story. In the early days of X-ray astronomy, before satellites made the job easier, scientists had to launch their instruments above Earth's atmosphere on short-lived sounding rockets, because X-rays from space are absorbed by our atmosphere and never reach the ground. Those rocket flights lasted only minutes, sometimes seconds of useful observation time, and the detectors were crude by modern standards. The fact that Cygnus X1 was detected at all during one of those brief rattling rides into the upper atmosphere is a testament to how intensely it radiates. It was, in a sense, screaming so loudly that even our most primitive instruments could hear it. Some early researchers quietly wondered whether such powerful X-ray sources might pose a radiation hazard to future astronauts, travelling through regions of the galaxy rich in compact objects. The consensus today is that the distances involved make the risk negligible, but the question was not unreasonable at the time, and it hints at a deeper anxiety that ran through early black hole research. The suspicion that these objects were not just scientifically interesting but existentially threatening. Cygnus X1 is still there, of course, still devouring gas from its blue supergiant companion, still flickering in X-rays, still quietly validating Einstein's equations, more than a century after they were written. In 2011, a refined measurement pinned its mass at about 21 solar masses and its distance at roughly 6,100 light-years from Earth. That is comfortably far, far enough that its gravitational influence on our solar system is precisely zero, but close enough that our instruments can study it in exquisite detail. It has become a laboratory, a place where theorists can test their models against real data, and it has delivered more surprises than anyone expected. Its spin, for instance, has been measured at over 95% of the theoretical maximum, meaning space-time around it is twisted into a vortex that would be nearly impossible to escape even from the ergosphere. It is not just a black hole, there's a black hole showing off. You linger for a moment, watching the accretion disk shimmer and churn, and then you notice something else in the distance. Another star, this one in the constellation Monoceros, the unicorn, which is already a wonderful name for a place harbouring a cosmic predator. It is closer to Earth than Cygnus X1, much closer, and for a long time it held the uncomfortable title of the nearest known black hole to our solar system. You set your course and begin to drift, because the next monster on our list has been lurking practically in our backyard. The constellation Monoceros is not one most people can pick out of the night sky. It sits in a dim, unassuming patch between Orion and Canis Major, the kind of celestial real estate that stargazers tend to skip over on their way to something flashier. But you are not most people tonight, and you are heading directly for it, because nestled within that faint stellar neighbourhood is an object catalogued as V616 Monocerotis, also known by its less romantic designation as 0620-00, and for decades it held the title of the closest known black hole to Earth, roughly 3,000 light-years away. In cosmic terms, that is practically next door. If the Milky Way were the size of the United States, 3,000 light-years would be about the distance from your couch to your kitchen. You would not even need to put shoes on. V616 Mono, as we will call it, because life is short and catalogue numbers are long, was first noticed in 1917 when it appeared as a faint nova on photographic plates. It flared, dimmed, and was largely forgotten, filed away in astronomical archives alongside thousands of other transient events that nobody had the technology to investigate further. Then, in 1975, it erupted again, this time brilliantly, becoming one of the brightest X-ray sources in the sky for a brief spectacular period before fading back into obscurity. That double outburst was suspicious. Normal novae, caused by thermonuclear explosions on the surface of white dwarf stars, do recur, but the X-ray profile of V616 Mono's eruptions did not match the white dwarf pattern. Something else was going on, something involving far more extreme physics, and by the early 1980s, astronomers had zeroed in on the culprit. The system contained a compact object with a mass of roughly 6 to 7 solar masses, well above the neutron star limit, orbiting a small companion star that was being slowly, methodically stripped of its outer layers. You arrive at the system and the scene is quietly horrifying. The companion star, a K-type dwarf about half the mass of our Sun, is visibly distorted. It is not spherical. It is egg-shaped, elongated toward the black hole by tidal forces, its outer atmosphere drawn into a teardrop that leaks matter in a thin glowing stream toward the accretion disk. This process is called Roche-Lobe overflow, named after the French astronomer Édouard Roche, who in the 19th century calculated the gravitational boundaries within which a smaller body can hold itself together in the presence of a larger one. When the companion star swells or drifts close enough that its outer layers spill beyond its Roche-Lobe, matter flows freely toward the black hole, feeding the accretion disk in a slow but relentless transfer that has been going on for millions of years. The companion star is being consumed, not in a dramatic gulp, but in a patient, almost gentle sip that will eventually reduce it to a stripped core, a skeletal remnant of what it once was. Here is the detail that makes V616 Mono particularly unsettling for anyone who enjoys sleeping at night. For a long time, this was considered the nearest black hole to our solar system, and the question of just how close the nearest black hole actually sits has haunted astronomers for decades. The Milky Way is estimated to contain somewhere between 100 million and 1 billion stellar mass black holes, a number that is deliberately vague because most of them are invisible, a black hole that is not actively feeding, not pulling gas from a companion star, not accumulating an accretion disk, produces no electromagnetic radiation whatsoever. It is dark. It is silent. It drifts through the galaxy like an unlit ship on a moonless ocean, detectable only by its gravitational influence on things that happen to pass nearby. The overwhelming majority of black holes in our galaxy are in this dormant state, which means we have no idea where most of them are. Scholars still argue about the true population, and the estimates vary by an order of magnitude depending on which stellar evolution models you trust and how generous you are with the initial mass function. That thought deserves a moment to settle in. You're lying in bed right now on a planet orbiting a perfectly ordinary star in a galaxy that contains possibly 1 billion black holes, and you cannot see almost any of them. The nearest one could be far closer than 3,000 light-years. In fact, in 2022, astronomers announced the discovery of Gaia BH1, a dormant black hole only about 1,600 light-years from Earth, quietly orbiting a sun-like star in the constellation Ophiuchus. It was found not by its X-ray emissions, because it has none, but by the wobble it induced in its companion star's motion, a gravitational signature detected by the European Space Agency's Gaia spacecraft. Then came Gaia BH2, even closer in some analyses, and suddenly V616 Mono lost its title as the nearest known black hole. The neighbourhood was getting crowded and the neighbours were not friendly. But let us stay with V616 Mono a moment longer, because its companion star tells a story that is both scientifically important and oddly poignant. That little K-dwarf is doomed. There is no rescue mission, no intervention, no cosmic restraining order that can stop the mass transfer. Over millions of years it will continue to lose matter, shrinking and cooling as its outer layers are peeled away and devoured. Eventually, it may be reduced to a brown dwarf or even a planetary mass remnant, a cold, dark husk orbiting the thing that ate it. And here is a quirky tidbit that researchers have noted. During the quiescent phases between outbursts, the accretion disk around V616 Mono becomes so faint that the system's total light is dominated by the companion star. You could point a modest telescope at this system and see what appears to be a perfectly normal, slightly dim star, with no hint that it is locked in a death spiral with one of the most destructive forces in the universe. The monster's right there, hiding in plain sight behind the glow of its victim. The 1975 outburst itself was a spectacular event. V616. Mono brightened by a factor of nearly 100,000 in visible light over the course of just a few days, making it temporarily one of the brightest objects in the sky at X-ray wavelengths. The outburst was caused by a sudden surge of matter through the accretion disk, a kind of gravitational traffic jam that released enormous amounts of energy as the backed-up material finally cascaded inward. These outbursts are called X-ray transients, and they provide some of the best opportunities to study black hole accretion in action. During V616 Mono's eruption, observers recorded rapid oscillations in the X-ray flux, flickering on timescales of milliseconds, which confirmed that the emitting region was tiny, compact, and consistent with matter spiraling into an event horizon. The data from that single event fed dozens of papers and helped establish the observational criteria that astronomers still use today to identify black hole candidates in binary systems. You watch the little K-dwarf star wobble on its distorted orbit, its surface rippling faintly as tidal forces tug at its gas, and you feel a strange sympathy for it. It did nothing wrong. It simply formed too close to something terrible, and now it is being slowly undone by the laws of physics. The universe is not cruel exactly. It is indifferent, which is somehow worse. You give the doomed star one last look, then turn your attention elsewhere. Because out there in the galactic plane, there is a black hole that does not just feed quietly. It throws tantrums. It fires jets of plasma at nearly the speed of light. It spins so violently that it warps space-time into a screaming vortex. And it has been putting on a show for astronomers since the early 1990s, behaving less like a stellar remnant and more like a miniature quasar trapped in our own galaxy. You feel it before you see it. A tremor in the starfield, a faint rippling of light as though someone dropped a stone into the surface of the universe, and the waves have not quite settled. You're approaching GRS 1915 plus 105, and this black hole does not believe in subtlety. It sits roughly 28,000 light-years from Earth, tucked deep in the galactic plane in the constellation Aquila the Eagle, and it has been confounding astrophysicists since its discovery in 1992 by the Granite Satellite's Watch instrument. What the satellite found was an X-ray source erupting with a ferocity that defied easy classification. It was not behaving like a well-mannered stellar mass black hole quietly sipping from a companion star. It was gorging, flaring, sputtering, and occasionally firing columns of superheated matter out into space at velocities that appeared, bafflingly, to exceed the speed of light. Now, before you panic, nothing is actually breaking the cosmic speed limit. The apparent superluminal motion is an illusion, a geometric trick caused by jets of plasma travelling at roughly 92 to 98% of the speed of light aimed nearly, but not quite, toward Earth. When material moves that fast at a shallow angle to your line of sight, the light from successive positions along the jet arrives at your telescope compressed in time, making the jet appear to cross the sky faster than light could. It is the same basic principle that makes a fire truck's siren sound higher as it approaches. The underlying physics is perfectly well behaved. The appearance, however, is alarming, and when the first measurements were published in 1994, they made headlines precisely because the phrase "faster than light" is irresistible to both journalists and clickbait algorithms, a tradition that continues robustly to this day. GRS 1915 plus 105 is what astronomers call a microquasar, a stellar mass black hole that mimics the behaviour of the supermassive monsters at the centres of distant galaxies, just scaled down. It has an accretion disk, it has relativistic jets, it has violent, unpredictable variability, and it has a mass of roughly 12 to 14 solar masses packed into an event horizon you could fit comfortably inside a mid-sized city. Its companion star is a low-mass giant that orbits the black hole every 33.5 days, close enough that mass transfer is constant and vigorous. The accretion disk around GRS 1915 plus 105 is one of the most dynamic structures ever observed, cycling through at least 14 distinct patterns of X-ray variability that astronomers have catalogued with the weary thoroughness of birdwatchers documenting species in a particularly chaotic aviary. Some patterns show steady emission, some show rapid-fire bursts, some show long, slow oscillations followed by sudden crashes. No other X-ray binary in the galaxy has displayed anything close to this variety, and the reasons are still not fully understood. Theorists argue about whether the variability is driven by instabilities in the accretion disk, fluctuations in the magnetic field geometry, or some interaction between the jets and the inflowing matter that creates feedback loops of dizzying complexity. The jets themselves are the main attraction. You watch them now, two narrow beams of plasma lancing outward from the poles of the accretion disk, punching through the surrounding interstellar medium like spotlights cutting through fog. The material in those jets is heated to temperatures exceeding 1 billion degrees, and it carries enough kinetic energy to inflate vast lobes of radio-emitting gas that extend for light years on either side of the black hole. In 1997, observations reveal that these jets are not continuous. They are episodic, launched in discrete blobs that travel outward and gradually decelerate as they slam into the interstellar medium. Each blob represents a violent ejection event, a moment when the accretion disk reorganized itself and flung excess material outward rather than letting it fall inward. It is as if the black hole periodically chokes on its meal and coughs part of it back up, which is a deeply undignified image for one of the most powerful objects in the galaxy, but also a fairly accurate one. Here is the historical context that makes GRS 1915+105 particularly important. Before its discovery, the phenomenon of relativistic jets was associated almost exclusively with active galactic nuclei, the supermassive black holes at the hearts of distant galaxies that power quasars and radio galaxies. The idea that a stellar mass black hole in our own Milky Way could produce miniature versions of the same jets was revolutionary. It established a direct physical link between the smallest and largest black holes in the universe, suggesting that the jet launching mechanism is fundamentally the same regardless of scale. This universality has become one of the most productive insights in modern astrophysics, because it means you can study the physics of jets in microquasars, where changes happen on human timescales of minutes and hours, and apply the lessons to supermassive systems where the same processes unfold over thousands of years. GRS 1915+105 became a Rosetta Stone, a translator between the stellar and the galactic, and its data has appeared in hundreds of papers across 3 decades of research. And then there is the spin. GRS 1915+105 rotates at nearly the maximum rate permitted by general relativity. Measuring black hole spin is notoriously difficult, because you cannot exactly walk up and attach a tachometer, but the technique involves analysing the X-ray spectrum reflected off the inner edge of the accretion disk. The closer that inner edge sits to the event horizon, the faster the black hole must be spinning, because a rapidly rotating black hole drags the innermost stable circular orbit inward through a phenomenon called frame dragging. For GRS 1915+105, the data suggests a spin parameter above 0.98, where 1.0 is the theoretical maximum. This means space-time near the event horizon is being whipped around at a substantial fraction of the speed of light. The ergosphere, that region outside the event horizon where nothing can stand still, extends dramatically, and the energy available for extraction through processes like the Penrose mechanism we discussed earlier is enormous. Some theorists believe the spin is precisely what powers the jets, that the rotational energy of the black hole itself is being tapped through magnetic field lines threading the event horizon, a process described by the Blandford-Znajek mechanism proposed in 1977. If that is correct, then GRS 1915+105 is not just consuming its companion star, it is using its own angular momentum as a weapon, converting spin into twin beams of destruction that reshape the surrounding galaxy. Here is a quirky footnote that rarely makes it into textbooks. In 2019, after decades of dramatic activity, GRS 1915+105 went quiet. Its X-ray flux dropped to the lowest levels ever recorded, and the once spectacular variability patterns vanished. Astronomers initially worried that the system had entered a fundamentally new state, perhaps exhausting its fuel supply or undergoing some structural change in the accretion disk. Subsequent observations suggested that the quiet phase was caused by a buildup of obscuring material around the system, a kind of cocoon of gas and dust that was absorbing the X-rays before they could reach our telescopes. The black hole was still feeding. It was just eating behind a curtain. Whether this obscured state is temporary or represents a longer-term change in the system remains an open question, and researchers are watching with the patient intensity of people who know the show is not over. You pull away from GRS 1915 plus 105, the afterimage of its jet still burning faintly in your mind's eye, and you set a course for something even more puzzling. Not far from here, at least not far by galactic standards, there is a black hole that caused an uproar when it was announced. A stellar mass object so massive that it seemed to violate everything we thought we knew about how stars die and black holes form. It was called LB1, and it arrived in the literature like a grenade tossed into a library. The grenade landed in November 2019, and the explosion was immediate. A team of astronomers led by Jifeng Liu at the Chinese Academy of Sciences published a paper announcing the discovery of a black hole in a binary system designated LB1, located about 15,000 light-years from Earth in the constellation Gemini. That alone would have been interesting but not extraordinary. What made the announcement detonate across the astrophysics community was the claimed mass. 70 solar masses, a stellar mass black hole 70 times heavier than our Sun, sitting right there in the Milky Way, orbiting a perfectly ordinary B-type star as though nothing were unusual. The problem was that everything about it was unusual because according to the prevailing models of stellar evolution, a black hole that massive should not have been able to form in a galaxy with our chemical composition. The announcement did not just challenge expectations, it kicked the table over and walked out of the room. You drift toward the system and try to understand why 70 solar masses cause such a fuss. The issue is metallicity, which in astronomy does not mean what it means in a hardware store. To an astrophysicist, any element heavier than helium is a metal, which means carbon, oxygen, nitrogen, iron, and everything else that makes up your body and your planet are all lumped under the same cheerfully imprecise label. Stars with high metallicity, stars formed in chemically enriched environments like our region of the Milky Way, lose mass aggressively through stellar winds during their lifetimes. These winds are driven by radiation pressure acting on the heavy elements in the star's outer layers, and they can strip away enormous amounts of material before the star ever reaches the supernova stage. The result is that by the time a massive star in a metal-rich environment collapses, its core is significantly lighter than the star's original mass. Models at the time suggested that this mass loss should cap stellar mass black holes in our galaxy at roughly 40 to 50 solar masses at most. 70 was not just above the limit, it was laughing at it. And remember that pair instability gap we talked about earlier, back when you were watching a star die. Stars in a certain mass range, roughly 65 to 130 solar masses, are predicted to be completely destroyed by pair instability supernovae, leaving no remnant at all. A 70 solar mass black hole sat right in the danger zone of that predicted gap, which meant either the pair instability models were wrong, the mass measurement was wrong, or something genuinely new and poorly understood was happening. The astrophysics community reacted with a mixture of excitement and deep skepticism, which is the healthiest possible response to an extraordinary claim, and within weeks the scrutiny began. The original mass estimate relied on radial velocity measurements of the companion star and what appeared to be a broad hydrogen alpha emission line attributed to the black hole's accretion disk. The logic was that by measuring the orbital motion of both the visible star and the disk, you could calculate the masses of both components. It was a sound technique in principle, but several independent teams quickly pointed out potential problems. One group argued that the broad emission line was not from the accretion disk at all, but was instead an artifact of the way the companion star's own absorption line had been subtracted from the spectrum. If that were the case, the inferred mass of the black hole would drop dramatically. Another team reanalyzed the data using different spectral models and found a mass closer to 25 solar masses, still hefty, but well within the range that conventional stellar evolution could explain. A third group raised concerns about the orbital inclination, noting that if the system were oriented differently than assumed, the mass estimate would shift substantially. Jifeng Liu and his colleagues responded to the criticism with revised analyses, and by 2020 the consensus had shifted. The black hole in LB1 was probably real, but its mass was likely in the range of 20 to 30 solar masses, rather than the headline-grabbing 70. The original paper was not retracted, but the extraordinary claim had been brought back to Earth, or at least back to the plausible part of the sky. Scholars still debate the exact mass and the precise mechanism by which the system formed, but the episode became a textbook example of how science is supposed to work. Bold claim, intense scrutiny, revised conclusion, continued investigation. The process was messy and public and sometimes heated, and it was beautiful in exactly the way that peer review is beautiful when it functions correctly. But here is the thing that makes the LB1 saga more than just a cautionary tale about premature press releases. The questions it raised were real, and they have not gone away. Even at 20 to 30 solar masses, the black hole in LB1 is on the heavy end of the stellar mass spectrum, and the broader question of how massive stellar mass black holes can get in metal-rich galaxies remains genuinely open. The detection of gravitational waves by the LIGO and Virgo observatories has complicated the picture enormously. In September 2020, the LIGO-Virgo collaboration announced the detection of GW 190521, a gravitational wave signal produced by the merger of two black holes with masses of approximately 85 and 66 solar masses. The resulting black hole was about 142 solar masses, the first ever detected in the intermediate mass range. Both of the merging black holes sat squarely inside the pair instability gap, which meant either they formed through some exotic pathway, perhaps the merger of smaller black holes in dense stellar environments, or the pair instability models themselves needed revision. The discovery sent theorists scrambling, and the scrambling has not stopped. Here is a fringe detail that adds spice to the story. Some researchers have proposed that the heavy black holes detected by LIGO could be primordial in origin, formed not from stellar collapse but from density fluctuations in the very early universe, mere fractions of a second after the Big Bang. If primordial black holes exist in the right mass range, they could pair up and merge in exactly the way LIGO observed, neatly sidestepping the pair instability problem entirely. The idea is speculative and far from mainstream, but it has gained enough traction to generate a healthy stream of papers and conference talks, and it connects the mystery of unexpectedly massive stellar black holes to one of the deepest questions in cosmology: what is dark matter made of? We will circle back to primordial black holes later, because they deserve their own spotlight in this journey. You linger near LB1, watching the B-type companion star trace its orbit around an invisible centre of mass, and you think about how much of the universe is defined by things we cannot directly see. The black hole reveals itself only through its influence, through the wobble it induces in its companion, through the faint X-ray whispers of accreting gas, through the gravitational waves it produces when it collides with something equally invisible. The universe is mostly dark. Most of its mass is in forms we cannot photograph or touch, and black holes are just the most dramatic example of a cosmos that prefers to operate behind the scenes. That thought should probably be unsettling. But by now you are getting comfortable with the darkness. It is just the way things are. And speaking of darkness, the next stop on our journey involves something even more unnerving than a black hole that is too massive. It involves black holes that have no home at all, no companion star, no galaxy centre, no fixed address. They are wanderers, drifters, gravitational ghosts roaming the Milky Way in silence, and the thought of them passing undetected through our stellar neighbourhood is the kind of thing that makes astronomers stare at their ceiling fans at 2 a.m. There is something uniquely disturbing about a predator that moves. A black hole anchored at the centre of a galaxy is terrifying, sure, but it is stationary. You know where it is. You can point at it on a chart and say, "There, that is where the monster lives, do not go there." A wandering black hole offers no such comfort. It has no fixed address, no orbit around a convenient companion star, no accretion disk announcing its presence in X-rays. It simply drifts through the galaxy like a dark marble rolling across an infinite table, invisible until it happens to pass close enough to something that its gravity gives it away. And the Milky Way, according to our best theoretical estimates, contains millions of them. You're floating now in the interstellar medium, that thin soup of gas and dust that fills the spaces between stars, and you're trying very hard not to think about what might be passing through the neighbourhood unannounced. The existence of wandering black holes is not speculative. It is a straightforward consequence of stellar evolution and galactic dynamics. When a massive star dies in a supernova, the explosion is not always symmetrical. If the blast is lopsided, the resulting neutron star or black hole receives a natal kick, a burst of momentum that sends it flying away from its birthplace at speeds that can reach hundreds of kilometers per second. For neutron stars, these kicks are well documented. Pulsars have been observed racing through the galaxy at remarkable velocities, clearly displaced from the supernova remnants that should have been their cradles. Black holes, being heavier, generally receive smaller kicks, but even a modest velocity is enough to unbind them from their birth clusters and send them wandering through the galactic disk for billions of years. The numbers are staggering if you sit with them for a moment. The Milky Way has been forming stars for roughly 13 billion years. In that time, every star above approximately 20 to 25 solar masses that has completed its life cycle has either produced a black hole or been destroyed entirely. Given the rate of star formation and the initial mass function, which describes how many stars of each mass are born in a given population, astrophysicists estimate that our galaxy alone hosts somewhere between 100 million and 1 billion stellar mass black holes. The vast majority of these are isolated. They are not in binary systems. They are not actively accreting matter. They emit no light, no X-rays, no radio waves. They are for all practical purposes invisible, and they are everywhere. Statistically, the nearest one could be as close as a few dozen light years, which is near enough that it would show up as a relatively bright star in our sky if it emitted any light at all. It does not. It is just gravity, moving silently through the dark. The first strong observational evidence for an isolated wandering black hole came in 2022, when 2 independent teams analysing data from the Hubble Space Telescope and ground-based microlensing surveys announced the detection of a free-floating compact object roughly 7 solar masses in size, located about 5,000 light-years from Earth. The detection method was gravitational microlensing, a technique that exploits the same light-bending physics that creates Einstein rings around black holes. When a massive object passes between a distant background star and the observer, its gravity acts as a lens, magnifying and brightening the background star's light in a characteristic symmetrical curve. The shape and duration of the brightening tell you the mass of the lensing object and its distance. In this case, the event lasted far longer than expected for a normal star, and the lensing object produced no detectable light of its own, which strongly suggested a black hole. The two teams initially disagreed on whether the object was definitively a black hole or possibly a very heavy neutron star, with mass estimates differing slightly depending on the modelling assumptions. Scholars continue to refine these measurements, and the object remains one of the most compelling candidates for an isolated stellar mass black hole ever identified. Here is a historical fact that grounds this in a longer scientific tradition. The possibility of detecting dark objects through gravitational lensing was first proposed in 1936 by Albert Einstein himself, though he dismissed the practical likelihood of ever observing such an event, writing that there was no great chance of it being detected. He was wrong, of course, spectacularly wrong, and the first microlensing events were observed in the early 1990s by survey projects specifically designed to find them. The technique has since become one of the most powerful tools in the search for dark compact objects, and large-scale surveys like the upcoming Vera C. Rubin Observatory's Legacy Survey of Space and Time are expected to detect thousands of microlensing events, some fraction of which will be caused by wandering black holes. The era of cataloguing the invisible population is just beginning. Now here is the question that tends to make people shift uncomfortably in their seats. What would happen if a wandering black hole entered our solar system? The short answer is that it depends on how close it comes and how massive it is, but the range of outcomes starts at mildly disruptive and escalates rapidly to extinction-level catastrophe. If a 10 solar mass black hole passed through the outer Oort cloud, roughly 50,000 astronomical units from the Sun, it would scatter comets inward, potentially triggering a bombardment of the inner solar system that could last millions of years. Closer than that, the gravitational perturbations would begin to affect planetary orbits. A passage within a few hundred astronomical units could destabilize the outer planets, sending Neptune or Uranus on chaotic trajectories that would ripple inward and eventually disrupt Earth's orbit. And if the black hole passed through the inner solar system itself, well, the results would be immediate and total. Tidal forces would distort the Sun, strip atmospheres from planets, and potentially eject Earth from its orbit entirely, sending it tumbling into the frozen dark of interstellar space. You would not be spaghettified, probably. The black hole would pass too quickly for that. You would just lose your star, your warmth, and your future, all in one gravitational breath. The probability of this happening is thankfully extraordinarily low. The galaxy is vast, the distances between objects are enormous, and even with 100 million wandering black holes out there, the odds of one passing close enough to our solar system to cause damage within the next several billion years are negligible. You're far more likely to be hit by a rogue asteroid, which is itself extremely unlikely, so you can unclench your jaw and let your shoulders drop back down from your ears. The universe is dangerous, but it is also mostly empty, and that emptiness is your best defense. But here is a quirky thought experiment that some researchers have entertained, largely in the spirit of scientific curiosity rather than genuine concern. If a wandering black hole were approaching our solar system, when would we detect it? The answer is unsettlingly late. Without an accretion disk or companion star, the black hole would be invisible to electromagnetic telescopes. Our first clue would be subtle perturbations in the orbits of distant Kuiper belt objects or Oort cloud comets, anomalies that would take years of careful observation to distinguish from normal gravitational noise. By the time we confirmed the cause, the black hole could be well on its way into the inner solar system. There is no alarm bell, no early warning system, no cosmic smoke detector for this particular threat. We would simply notice one day that something was very slightly wrong with the trajectories of distant ice balls, and then gradually that the wrongness was getting closer. It is the astronomical equivalent of hearing a floorboard creak in an empty house and deciding it was probably the wind. You shiver, though there is no wind in space, and you turn your attention toward a different mystery. Somewhere between the stellar mass black holes you have been visiting and the supermassive giants lurking in galactic cores, there is a gap. A missing population. Black holes of intermediate mass, hundreds to thousands of solar masses that theory predicts should exist, but that have proven maddeningly difficult to find. The hunt for these middleweight enigmas has frustrated astronomers for decades, and the story of that search is its own kind of thriller. You have spent the last stretch of this journey meeting black holes that fall into two neat categories. The stellar mass variety, born from the deaths of massive stars, weighing in at roughly 5 to perhaps 50 or 60 solar masses, and the supermassive variety, which we have not visited yet but which you have heard whispers about, millions to billions of solar masses heavy, sitting enthroned at the centres of galaxies. Between those two populations there should be a middle class, an intermediate range from about 100 to 100,000 solar masses, populated by black holes too heavy to have formed from a single star's collapse but too light to qualify as supermassive. Logic says they should exist, simulations predict them, and yet, for decades, the observational evidence for intermediate mass black holes has been frustratingly thin, like trying to prove the existence of a species you have only ever seen in blurry photographs taken from very far away. The problem is detection. Stellar mass black holes reveal themselves when they're in binary systems, feeding from companion stars and producing telltale X-ray signatures. Supermassive black holes announce their presence through the violent activity at galactic centers, through quasars and jets, and the frantic orbits of nearby stars. Intermediate mass black holes, if they exist in the expected numbers, likely inhabit environments where neither of these detection methods work particularly well. They might sit at the centers of globular clusters, those ancient densely packed balls of stars that orbit galaxies like satellites. They might drift through galactic halos, accumulated through mergers of smaller black holes over billions of years. They might lurk in dwarf galaxies too faint and distant for our current instruments to probe in detail. In every case, the signal they produce is subtle, ambiguous, and easily confused with other phenomena. Hunting for intermediate mass black holes is like trying to hear a whisper in a crowded room where everyone else is politely but firmly talking about something unrelated. The most famous candidate for an intermediate mass black hole is an object called HLX-1, short for Hyperluminous X-ray Source 1, discovered in 2009 near the edge of the galaxy ESO 243-49, roughly 290 million light-years from Earth. SRJ-LYAC. One caught attention because its X-ray luminosity was far too high to be explained by a stellar mass black hole, accreting at normal rates. The maximum luminosity at which a black hole can steadily accrete matter is called the Eddington limit, named after the British astrophysicist Arthur Eddington, who in the 1920s calculated the point at which radiation pressure from infalling matter balances gravitational attraction, exceed the Eddington limit, and the radiation blows the accreting material away, shutting off the fuel supply. For a stellar mass black hole of 20 solar masses, the Eddington luminosity is substantial but finite. HLX-1 was shining at X-ray luminosities that implied a mass of roughly 20,000 solar masses, assuming it was accreting at or below its Eddington limit. That placed it firmly in intermediate mass territory and made it the single best candidate in the sky. But even HLX-1 has not escaped controversy. Some researchers have argued that the luminosity could be explained by a stellar mass black hole accreting at super Eddington rates, a process in which the geometry of the accretion flow changes to allow more matter to fall in than the classical limit would suggest. Others have questioned the distance estimate to the host galaxy, noting that if HLX1 were closer than assumed, its luminosity and therefore its inferred mass would be lower. The debate has been ongoing for over a decade, and while the majority of the community leans toward the intermediate mass interpretation, the case is not closed. Scholars still argue about whether any single observation constitutes definitive proof, and the bar for definitive proof in this field is exceptionally high, partly because the implications are so significant. Why does the existence of intermediate mass black holes matter so much? Because they are the missing link in our understanding of how supermassive black holes form. This is one of the great unsolved puzzles in astrophysics, and it has been nagging at researchers since the discovery that quasars, powered by supermassive black holes, existed when the universe was less than 1 billion years old. That is an astonishingly short time for a black hole to grow from stellar mass to billions of solar masses. Even if a seed black hole accreted matter continuously at the Eddington limit from the moment it formed, the math barely works, and continuous Eddington rate accretion for hundreds of millions of years is physically implausible. Something else must be going on. One possibility is that supermassive black holes grew from much larger seeds, intermediate mass black holes of perhaps 1,000 to 100,000 solar masses that formed through exotic processes in the early universe. These seeds could have been produced by the direct collapse of massive primordial gas clouds, clouds so large that they skipped the normal star formation process entirely, and collapsed straight into black holes without ever igniting nuclear fusion. Another possibility is that intermediate mass black holes form through repeated mergers in dense stellar environments, growing incrementally over time like a snowball rolling downhill through a field of smaller snowballs. Here is a historical nugget that adds context. The concept of a black hole more massive than a star but less massive than a galaxy centre was first seriously discussed in the 1970s. But observational searches did not begin in earnest until the late 1990s, when X-ray telescopes like Chandra and XMM Newton provided the sensitivity needed to detect faint, off-centre X-ray sources in nearby galaxies. Before that, the intermediate mass range was essentially a theoretical placeholder, a blank space on the map labelled "This be dragons," or more accurately, "Here should be dragons, but we cannot find them." The gap between theory and observation became a source of genuine frustration, and some researchers began to wonder whether the formation channels for intermediate mass black holes were simply less efficient than the models predicted, resulting in a population too sparse and too quiet to detect with existing technology. And then gravitational waves changed everything. Remember GW190521, the signal we mentioned during the LB1 discussion, the merger that produced a black hole of roughly 142 solar masses. That remnant was, by definition, an intermediate mass black hole, and its detection by LIGO and Virgo in 2019 provided the first clean, unambiguous evidence that objects in this mass range exist. The signal was brief, just a few cycles of gravitational wave oscillation, lasting about 1/10 of a second, but it was enough. The masses of the two merging black holes and the final remnant were extracted from the waveform with remarkable precision, and there was no ambiguity about the result. The astrophysics community exhaled collectively, because after decades of searching in electromagnetic wavelengths and finding only candidates and controversies, the gravitational wave universe had delivered the answer in a single clean chirp. Here is a quirky footnote to the intermediate mass saga. Some theorists have proposed that globular clusters, those ancient stellar cities orbiting our galaxy, might each harbour an intermediate mass black hole at their centre, grown through repeated mergers over billions of years. If true, the Milky Way's roughly 150 known globular clusters would represent 150 intermediate mass black holes, hiding in plain sight within objects that amateur astronomers photograph for fun on clear nights. The evidence is mixed. Some clusters show dynamical signatures consistent with a central massive object. Others do not. The debate is ongoing, and every new dataset shifts the balance slightly in one direction or another. It is one of those problems where the answer feels tantalizingly close, but never quite arrives, like waiting for a bus that the schedule insists should have been here 10 minutes ago. You leave the intermediate mass puzzle behind, unsolved but illuminated, and you turn your gaze inward. Not inward in a philosophical sense, though that would be appropriate given the hour, but inward toward the centre of our own galaxy, 26,000 light-years away, hidden behind vast clouds of interstellar dust that block visible light entirely. Something enormous and patient is waiting. It has a name, it has a mass, and it has been shaping the Milky Way since long before our sun was born. You cannot see it with your eyes. That is the first thing to understand. If you stood outside on the clearest, darkest night imaginable and aimed a perfect optical telescope toward the constellation Sagittarius, you would see nothing but dense, glowing river of stars and dust, the bright central bulge of the Milky Way. Behind that luminous curtain, buried under roughly 25 magnitudes of visual extinction from intervening gas and dust, sits the gravitational heart of our galaxy. It is called Sagittarius A star, often written as S-Gray, and it is a supermassive black hole approximately 4 million times the mass of our Sun. It is not the largest supermassive black hole known, not even close, but it is ours, and there is something profoundly eerie about knowing that the galaxy you live in is built around a monster. The journey to confirming S-Gray as a black hole is one of the great detective stories in modern astronomy, and it took decades of painstaking work. The first hint came in 1974, when astronomers Bruce Ballack and Robert Brown detected a compact, unusual radio source at the galactic centre. The source was bright, point-like, and unlike anything else in the region. Brown gave it the name Sagittarius A star, appending the asterisk to distinguish it from the larger Sagittarius A radio complex surrounding it. The name stuck, asterisk and all, and it has been confusing people who are not astrophysicists ever since. For years, the nature of the radio source remained uncertain. It could have been an unusual stellar object, a dense cluster of something exotic, or a black hole. The technology of the 1970s simply could not resolve the question. The breakthrough came through patience and orbital mechanics. Beginning in the early 1990s, two independent teams, one led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics and the other by Andrea Ghez at UCLA, began tracking the motions of individual stars near the galactic centre, using infrared telescopes that could peer through the dust. Infrared light, with its longer wavelength, slips past the intervening material that blocks visible light, and with adaptive optic systems that correct for atmospheric turbulence in real time, the teams achieved resolutions sharp enough to pick out individual stars in the crowded central cluster. Year after year, they returned to their telescopes and plotted the positions of these stars, building up orbital tracks with the meticulous patience of someone assembling a 10,000-piece puzzle in a dimly lit room. The star that clinched the case is called S2, or S0-2 depending on which team's naming convention you prefer, and its orbit is breathtaking. S2 is a young, blue, massive star that whips around SGR-A star on a highly elliptical orbit with a period of roughly 16 years. At its closest approach, called pericenter, S2 passes within about 120 astronomical units of the black hole, which is roughly 4 times the distance from the Sun to Neptune. At that point, it is travelling at nearly 3% of the speed of a light, almost 8,000 kilometers per second, fast enough to cross the continental United States in less than a second. The gravitational field it experiences at pericenter is so intense that its light is measurably redshifted by gravitational time dilation, an effect predicted by general relativity that was confirmed using S2's orbit in 2018. Both Genzel and Ges shared the Nobel Prize in Physics in 2020 for this work, alongside Roger Penrose, who was recognised for his theoretical proof that black hole formation is a robust prediction of general relativity. It was by any measure a well-deserved triple honour. The mass of SGR-A star is determined directly from the orbits of S2 and its neighbours. Kepler's laws, generalised by Einstein, allow you to calculate the mass of a central body if you know the period and shape of an orbiting object's path. The result is approximately 4.15 million solar masses concentrated within a region no larger than the orbit of Mercury. No known physical object other than a black hole can pack that much mass into that smaller volume. A dense cluster of neutron stars or other exotic objects would be gravitationally unstable and would collapse or disperse on timescales far shorter than the age of the galaxy. The conclusion is essentially inescapable. SGR-A star is a supermassive black hole, and yet for all its mass, SGR-A star is remarkably quiet. Compared to the supermassive black holes powering distant quasars, our galaxy's central engine is practically in hibernation. Its luminosity across all wavelengths is roughly 100 million times lower than what it could produce if it were accreting at its Eddington limit. It is, in technical terms, a low-luminosity active galactic nucleus, the astronomical equivalent of a sleeping dragon. Small amounts of gas do trickle inward from the winds of nearby massive stars, forming a thin, hot, disorganized accretion flow that glows faintly in radio and X-rays, but the feeding rate is pitiful compared to the black hole's capacity. If SGR-A were a bathtub, the faucet would be dripping once an hour. This has not always been the case. Here is a historical fact that adds a dramatic twist. In 2010, NASA's Fermi Gamma Ray Space Telescope discovered two enormous structures extending above and below the galactic plane, each stretching roughly 25,000 light-years from the centre. These are called the Fermi Bubbles, and they are believed to be the remnants of a massive energy injection from Skua star sometime in the past few million years. The leading interpretation is that our black hole experienced a period of much more vigorous accretion, perhaps triggered by a large cloud of gas falling inward, and the resulting outburst inflated these colossal bubbles of hot, gamma-ray emitting gas. If that interpretation is correct, then Skua star was significantly more active in the recent cosmic past, and the peaceful slumber you observe today is a temporary state, not a permanent one. Here is a quirky detail that makes the galactic centre even stranger. In 2011, astronomers discovered a mysterious object called G2 approaching SGR-A star, on a trajectory that would bring it within about 200 astronomical units of the black hole. Initially thought to be a simple gas cloud, G2 was expected to be torn apart by tidal forces during its closest approach in 2014, potentially providing a front-row seat to watch SGR-A wake up and feed. Telescopes around the world trained on the galactic centre in anticipation, and then almost nothing happened. G2 passed through pericenter largely intact, stretching and distorting but not breaking apart. Subsequent analysis suggested that G2 might not be a simple gas cloud at all, but rather a pair of merged stars surrounded by a bloated envelope of gas, compact enough to resist the tidal shredding that would have destroyed a diffuse cloud. The event was, scientifically, a fascinating surprise, but for the astronomers who had been hoping to see the black hole feast, it was the cosmic equivalent of ordering a fireworks show and getting a sparkler. Scholars still argue about the exact nature of G2, and the broader question of what triggers episodes of enhanced activity in SGR-A star remains wide open. The black hole sits at the center of a dense, chaotic stellar environment where molecular clouds, stellar winds, and gravitational interactions conspire to create a constantly shifting supply of potential fuel. One day, perhaps millions of years from now, something substantial will fall in, and A star will flare back to life, briefly transforming the heart of our galaxy into something resembling the violent active nuclei we observe in distant galaxies. When that happens, the Milky Way will look very different from the outside. But for now, the dragon sleeps, and you drift past it with quiet reverence, heading outward toward a galaxy far away, where a much larger black hole does not sleep at all and has already had its portrait taken. 55 million light years. That is how far you are about to travel, and you are going to do it in the space between one breath and the next. Because this is imagination, and imagination does not bother with speed limits. Your destination is a galaxy called Messier 87, or M87, a colossal elliptical galaxy sitting near the center of the Virgo cluster, a gravitational congregation of roughly 2,000 galaxies bound together in a slow, majestic dance. M87 is not a subtle galaxy. It contains several trillion stars dwarfing our Milky Way, and at its heart sits one of the most massive black holes ever measured, a beast weighing in at approximately 6.5 billion solar masses. That is not a typo. 6.5 billion suns, compressed into a region of space-time smaller than our solar system. And in April 2019, humanity saw its face for the first time. You arrive at the outskirts of M87, and the view is already overwhelming. The galaxy is a vast golden haze of ancient stars, mostly old red and yellow populations that give it a warm, almost autumnal glow. There are no dramatic spiral arms here, no bright lanes of star formation. Elliptical galaxies are the retirement communities of the cosmos, gravitationally relaxed, dynamically settled, their star-forming days largely behind them. But at the centre, something is very much not retired. A narrow, blazing jet of plasma extends from the galactic core outward for roughly 5,000 light-years, visible even in amateur telescopes as a faint blue streak against the amber background. That jet was first observed in 1918 by astronomer Heber Curtis at Lick Observatory, who described it as a curious straight ray extending from the galaxy's nucleus. He had no idea what he was looking at. It would take most of a century before astronomers understood that the ray was a relativistic jet, a stream of charged particles accelerated to nearly the speed of light by the magnetic fields threading the accretion disk of a supermassive black hole. Curtis was staring at the exhaust plume of one of the most powerful engines in the observable universe and had no framework to comprehend it. Science sometimes moves at the pace of a glacier, and this was one of those times. The Event Horizon Telescope, or EHT, changed everything. The EHT is not a single telescope. It is a planet-sized virtual observatory, created by linking radio dishes across the globe, from Hawaii to Spain, from the South Pole to Chile, into a synchronized network that functions as a single instrument with an effective diameter equal to the Earth itself. The technique is called Very Long Baseline Interferometry, and it achieves angular resolution so fine that it could, in principle, read the date on a coin in New York from a cafe in Paris. The EHT collaboration, involving over 200 scientists from dozens of institutions, spent years preparing to aim this extraordinary instrument at two targets, SGR A star at the center of our galaxy and M87 star at the center of Messier 87. On April 10th, 2019, they released the result for M87 star first, and the image burned itself into the collective consciousness of the planet. What you saw, what the entire world saw, was a bright, slightly asymmetric ring of light surrounding a dark central shadow. The ring was not the event horizon itself. It was the glowing accretion disk and the photons orbiting just outside the event horizon, their paths bent into a circle by gravity so intense that light literally travels in closed loops. The dark shadow in the centre was the silhouette of the event horizon against this bright background, the region from which no light escapes. The asymmetry of the ring, brighter on one side than the other, was caused by relativistic beaming. The side of the accretion disk moving toward Earth had its light amplified by the Doppler effect, while the receding side was dimmed. Every feature of the image matched the predictions of general relativity with remarkable precision. Einstein, who had been dead for 64 years, was still passing tests. The technical achievement required to produce that image was staggering. The raw data from the EEHT observations filled literal tons of hard drives that had to be physically shipped to central processing locations because the volume was too large to transmit over the internet. The observations were taken over a period of several nights in April 2017, and the data processing took 2 years. Atmospheric conditions, clock synchronization, calibration of dishes operating in different weather on different continents, all of these factors had to be accounted for with excruciating precision. And here is a detail that deserves more attention than it usually gets. The image you saw was not a photograph in the traditional sense. It was a reconstruction, assembled from sparse interferometric data using sophisticated algorithms. One of those algorithms, called CHIRP, was developed in part by Katie Booman, then a graduate student at MIT, whose work on imaging techniques became central to the reconstruction process. Bowman became briefly famous when a photograph of her reacting to the first image went viral, and then, because the internet is the internet, she became the target of absurd conspiracy theories claiming she did not deserve credit. The scientific community rallied around her, and the episode became an unfortunate but instructive lesson about the way public attention can distort the collaborative reality of large-scale science. Here is a quirky detail about M87 star that makes it even more extraordinary. The black hole is spinning, and the direction of its spin axis appears to be misaligned with the jet by a noticeable amount. This misalignment has puzzled researchers because most models predict that the jet should be launched along the spin axis. Some theorists have proposed that the misalignment is evidence of a past merger with another supermassive black hole, an event that could have tilted the spin axis relative to the large-scale structure of the galaxy. If true, M87 star carries the gravitational memory of an ancient collision, a scar from a time when two galaxies merged and their central black holes spiraled together and became one. The forensic work of reading these scars is still in its early stages, and scholars debate whether the misalignment is real, an artifact of modelling assumptions, or evidence of more complex accretion dynamics that do not require a merger explanation at all. The mass of M87 star, 6.5 billion solar masses, places it among the most massive black holes known, but it does not hold the record, not even close. The event horizon of M87 star has a diameter roughly the size of our entire solar system, edge to edge, which means that if you placed it where our Sun is, the boundary of no return would extend well past Pluto and into the Kuiper belt. Light takes about a full day to cross it. Inside that boundary, an amount of matter equivalent to 6.5 billion stars like our Sun has been compressed into a singularity, a point of theoretically infinite density where our understanding of physics breaks down completely. General relativity describes the geometry outside the event horizon with exquisite accuracy, but at the singularity itself the equations produce infinities, which is nature's way of telling you that your theory is incomplete. What actually happens at the centre of M87 star, whether there is a true singularity or some quantum gravitational structure that prevents infinite compression, is one of the deepest open questions in all of physics. We will return to this mystery later when we wade into the information paradox and the firewall debate, but for now it is enough to know that the centre of M87 star is where known physics goes to surrender. You linger at the edge of M87's luminous halo, watching the jet streak outward like a lighthouse beam frozen in time, and you feel the weight of 6.5 billion suns pulling at your imagination. This is enormous, this is humbling, and yet, as you're about to discover, M87 star is a middleweight compared to what comes next. Out there, in the distant reaches of the observable universe, there are black holes so massive that they make M87 star look modest. Black holes that power quasars bright enough to outshine entire galaxy clusters. Black holes whose very existence pushes the boundaries of what we thought the universe could produce. One of them has a name that sounds like a license plate, and its mass is genuinely difficult to comprehend. The name is TON 618, and it does not care about your sense of scale. You have spent this journey gradually adjusting your mental framework, stretching your imagination from stellar mass black holes of 10 or 20 suns to the 4 million solar mass anchor of our galaxy, to the 6.5 billion solar mass portrait subject in M87. Each step felt like a leap. Each new number seemed absurd until you sat with it long enough to let it settle. But TON 618 is going to break your scale entirely, because this object has a mass of roughly 66 billion solar masses, and it powers a quasar so luminous that it outshines everything around it with a cold, ancient fury that has been travelling toward your eyes for over 10 billion years. TON 618 was first catalogued in 1957 as part of the Tonantzintla Observatory Survey in Mexico, a project that photographed large swathes of the sky and recorded objects of interest for later study. At the time, it appeared to be nothing more than a faint bluish point of light, indistinguishable from thousands of other dim objects scattered across the photographic plates. It was not until 1970 that radio observations revealed it to be a quasar, one of those impossibly bright beacons powered by matter, falling into a supermassive black hole at the centre of a distant galaxy. The quasar sits at a redshift of about 2.2, which places it roughly 10.4 billion light-years from Earth. You're seeing it as it was when the universe was less than a third of its current age. The light now reaching your eyes began its journey before our sun existed, before the Earth coalesced from a disk of gas and dust, before the Milky Way had settled into its current graceful spiral. TON 618 has been burning since before our corner of the cosmos was even a rough draft. The luminosity is staggering. TON 618 radiates at approximately 140 trillion times the luminosity of our sun. Let that number wash over you for a moment without trying to picture it, because picturing it honestly is not possible. The entire Milky Way with its several hundred billion stars produces a combined luminosity that TON 618 exceeds by a factor of roughly 400, a single object outshining 400 galaxies. The energy source is gravitational. Matter from the surrounding environment, gas, dust, the shredded remains of stars that wandered too close, spirals into the accretion disk surrounding the black hole and is heated to temperatures of millions of degrees by friction and compression. The resulting radiation pours outward across the electromagnetic spectrum, from radio waves through infrared, visible light, ultraviolet, and X-rays, creating a beacon that is visible across cosmological distances. If you place TON 618 at the centre of our galaxy, replacing quiet little SG star, the night sky on Earth would be transformed beyond recognition. The galactic centre would blaze with a light rivaling the sun, and the radiation environment throughout the Milky Way would be altered in ways that would almost certainly be incompatible with life as we know it. The mass estimate of 66 billion solar masses comes from the width of broad emission lines in the quasars spectrum. When gas in the accretion disk and the surrounding broadline region moves at high velocities under the influence of the black hole's gravity, the spectral lines it produces are Doppler broadened, smeared out by the range of velocities present. The wider the lines, the faster the gas is moving, and the faster the gas is moving, the more massive the central black hole must be to keep it in orbit. This technique, called reverberation mapping in its more sophisticated form, has been refined over decades and cross-checked against other mass estimation methods, and while the uncertainties are real, they are not large enough to bring TON 618's mass below the jaw-dropping range. 66 billion solar masses is a conservative figure. Some analyses have suggested it could be even higher, though scholars debate the exact number depending on which modelling assumptions they favour and how they account for the geometry of the emitting gas. Here is where the numbers become not just large but geometrically absurd. The Schwarzschild radius of TON 618, the radius of its event horizon assuming it is not spinning, is approximately 194 billion kilometres. For reference, the distance from the Sun to Pluto at its farthest point is about 7.5 billion kilometres. The event horizon of TON 618 could swallow our entire solar system roughly 13 times over. If you replace the Sun with TON 618, the event horizon would extend far past the heliopause, the boundary where the solar wind gives way to interstellar space. Every planet, every asteroid, every comet, every grain of dust in the solar system would be comfortably inside the point of no return. The word comfortable is doing some dark work in that sentence, but the geometry is accurate. You, sitting on Earth, would already be well within the event horizon, falling inward without even feeling it, because at this scale, remember, the tidal forces near the horizon are gentle. You would be doomed but not spaghettified. You would simply be unable to leave, drifting toward a singularity whose nature nobody understands, with all the time in the world to contemplate the situation and no way to share your findings with anyone outside. Here is a historical fact that grounds TON 618 in the broader story of quasar discovery. Quasars were first identified in the early 1960s, when radio astronomers found compact, extraordinarily bright radio sources that appeared star-like in optical telescopes, but had spectral redshifts that placed them at cosmological distances. The first to be recognised was 3C273, identified by Martin Schmidt in 1963. Schmidt's realization that the strange emission lines in 3C273's spectrum were simply common hydrogen lines shifted to extreme redshifts was a eureka moment that revealed quasars to be the most luminous sustained objects in the universe. Before Schmidt's insights, some astronomers had proposed that these objects might be nearby and relatively mundane. After it, the universe suddenly became a much larger, more violent and more luminous place than anyone had imagined. And here is a quirky footnote about TON 618 specifically. Despite being one of the most powerful objects in the observable universe, it was effectively ignored for over a decade after its initial cataloguing. The 1957 survey that first recorded it was designed to find blue stars, not distant quasars, and the faint blue dot on the photographic plate attracted no special attention. It was just one entry among thousands. The realization that it was a quasar came only after radio surveys provided the context needed to recognize its true nature. This pattern, profound discoveries hiding in plain sight within existing data, is a recurring theme in astronomy. The universe is not secretive, it is generous with its signals. We're simply not always paying attention, or we lack the framework to recognize what we're seeing. TON 618 sat quietly in a filing cabinet for 13 years before anyone understood that it was one of the most remarkable objects ever recorded. You float in the quasar's distant glow, feeling the ancient light wash over you, and you try to hold the number in your mind. 66 billion suns. A single entity, forged from the accumulated mass of an entire galactic core's worth of stars and gas, compressed into a region defined by an event horizon the size of a small solar system. It is the kind of object that makes you reconsider the word terrifying, because terror implies a human-scale threat, and TON 618 is so far beyond human scale that it almost loops back around to serenity. Almost, but not quite, because somewhere out there, discovered more recently and measured with growing confidence, is a black hole that makes TON 618 look merely enormous. A black hole with a mass that redefines the upper limit of what the universe is capable of building. Its name is Phoenix A, and it is waiting for you at the center of a galaxy cluster that glows with the heat of unimaginable violence. You leave TON 618 behind, its ancient quasar light fading against your back like a lantern receding down an endless hallway, and you push deeper into the cosmos. Your destination now is not a single galaxy, but a galaxy cluster. A vast gravitational metropolis called the Phoenix Cluster, located roughly 5.7 billion light-years from Earth in the constellation Phoenix. Galaxy clusters are the largest gravitationally bound structures in the universe, collections of hundreds or sometimes thousands of galaxies held together by dark matter and threaded with superheated gas that glows in X-rays. The Phoenix Cluster is among the most massive and most luminous of its kind, a sprawling cosmic city that was already remarkable before anyone looked closely at the black hole sitting at its center. When they did look, in 2022, what they found reset the upper boundary of how massive a black hole can be. The black hole is called Phoenix A, and its estimated mass is roughly 100 billion solar masses. You can let that number land softly if you need to, because absorbing it quickly is not really possible. 100 billion suns. If TON 618 at 66 billion solar masses was hard to picture, Phoenix A is the point where the human brain politely declines to participate. The event horizon of Phoenix A, calculated from its mass, would stretch across a region so vast that light would take weeks to cross it. Our entire solar system, that familiar arrangement of planets and comets and Kuiper belt objects that constitutes everything most humans will ever consider home, would be a speck of dust lost inside it. Phoenix A does not just swallow solar systems, it swallows the spaces between them. The discovery was announced by a team led by astronomers at the University of Toronto, who measured the black hole's mass using stellar kinematics, the same fundamental approach that Genzel and Ghez used for SGR-A, but applied at a vastly larger scale. By measuring the velocities of stars in the central galaxy of the Phoenix cluster, they could infer the mass of the central object required to produce those velocities. The result was startling not just for its size, but for what it implied about the relationship between black holes and their host galaxies. There's a well-known correlation in astrophysics between the mass of a supermassive black hole and the mass of the stellar bulge of its host galaxy. This correlation, discovered independently by several groups around the year 2000, suggests a deep connection between the growth of black holes and the growth of galaxies, as though the two evolve in tandem, regulating each other through feedback processes involving jets, radiation, and gas dynamics. Phoenix A appears to sit above this correlation, meaning it is more massive than you would predict based on the size of its host galaxy alone. Whether this represents a genuine outlier, a measurement uncertainty, or a clue that the correlation breaks down at the highest masses is an active area of research that scholars continue to debate with considerable enthusiasm. The Phoenix cluster itself provides context for how such an enormous black hole might have formed. The central galaxy, designated BCG for brightest cluster galaxy, sits at the gravitational bottom of the cluster's potential well. Over billions of years, gas from the surrounding intracluster medium, that vast ocean of superheated plasma filling the space between galaxies, has been cooling and falling inward, feeding the central galaxy and its black hole. The Phoenix cluster is notable for having one of the highest cooling rates ever measured, meaning gas is condensing out of the hot intracluster medium and flowing toward the center at a rate of hundreds or even thousands of solar masses per year. That is an extraordinary fuel supply, and it helps explain how Phoenix A grew to its current monstrous size. It has been drinking from a fire hose for billions of years. Here is a mainstream historical fact that ties into this story. The idea that cooling gas in galaxy clusters could feed central black holes and trigger bursts of star formation was first developed in the 1970s and 1980s, when X-ray observations from the Einstein Observatory revealed that the centers of many clusters were cooler than their outskirts. These cool core clusters, as they came to be called, seemed to be losing energy through radiation faster than any known process could replenish it, which implied that the gas should be cooling catastrophically and raining down onto the central galaxy in enormous quantities. The predicted rates of star formation in these cooling flows far exceeded what was actually observed, creating a puzzle known as the cooling flow problem. The resolution, developed over the following decades, involved feedback from the central black hole. When enough gas accumulates and feeds the black hole, the resulting jets and radiation heat the surrounding gas, slowing or stopping the cooling flow until the black hole's activity subsides and the cycle begins again. This self-regulating loop, called a GN feedback, is now considered one of the most important processes governing the evolution of massive galaxies and galaxy clusters. Phoenix A sits at the violent heart of one of the most extreme examples of this feedback cycle ever observed. And here is a quirky detail that adds another dimension. The central galaxy of the Phoenix cluster is forming stars at a rate of roughly 500 to 800 solar masses per year, one of the highest star formation rates ever observed in the nearby universe. For comparison, the Milky Way forms new stars at a rate of about 1 to 3 solar masses per year. The Phoenix cluster's central galaxy is producing new stars hundreds of times faster than our entire galaxy, fueled by the same cooling gas that feeds the black hole. This vigorous star formation was unexpected because AGN feedback was supposed to suppress it. Either the feedback from Phoenix A is insufficient to quench the cooling flow completely, or the system is caught in a particularly active phase of the feedback cycle, a moment when the gas has overwhelmed the black hole's regulatory efforts and is pouring in faster than jets can push it back. Some researchers have suggested that the Phoenix cluster represents a rare glimpse of a feedback cycle caught in the act of failing, a cosmic thermostat that has temporarily lost control. Scholars still argue about whether Phoenix A's mass will hold up as measurements are refined. 100 billion solar masses is so far above previous records that healthy skepticism is warranted, and future observations with next-generation telescopes will be needed to confirm or revise the estimate. But even the lower bounds of the uncertainty range place Phoenix A firmly in ultra-massive territory, well above TON 618, and in a class that forces theorists to reconsider the maximum possible mass of a black hole. There are theoretical limits set by the available fuel supply in the age of the universe, but Phoenix A pushes uncomfortably close to those limits, raising the question of whether there are even larger black holes hiding in clusters we've not yet surveyed with sufficient resolution. You drift away from the Phoenix cluster, its X-ray glow softening behind you, and you carry with you the staggering arithmetic of 100 billion suns condensed into darkness. The journey so far has taken you from stellar corpses to galactic anchors to ultra-massive titans, and each step has revealed a universe more extreme than the last. But black holes are not just about mass. They're about what they do with that mass, how they interact with their surroundings, how they shape galaxies and illuminate the cosmos. And no class of objects demonstrates this more dramatically than quasars, those brilliant beacons that turn supermassive black holes into the brightest lighthouses in the universe. The universe was young and violent and magnificent, and you are now rewinding the clock to witness it. You have drifted backward through cosmic time, billions of years into the past, to an era when galaxies were still assembling themselves from clouds of primordial gas, when collisions between proto-galaxies were common and catastrophic, and when the supermassive black holes at the centres of these young galaxies were feeding. With an appetite that makes anything in the modern universe look polite by comparison. This is the age of quasars, and it was spectacular. A quasar at its core is simply a supermassive black hole that is actively accreting matter at a ferocious rate. The word itself is a contraction of quasi-stellar radio source, a name coined in the early 1960s when these objects were first discovered and nobody quite knew what to make of them. They looked like stars in optical telescopes, tiny points of light with no visible structure. But their spectra were bizarre, filled with emission lines that did not match any known element at any known redshift. It was Martin Schmidt's 1963 breakthrough with 3C273 that cracked the code, as we touched on earlier, and revealed that these strange objects were not nearby stars but incredibly distant galaxies, whose central engines were so luminous that they drowned out the light of hundreds of billions of surrounding stars. The galaxy was there. You just could not see it behind the glare. The mechanism is gravitational potential energy converted into radiation with an efficiency that shames every other energy source in the universe. When matter falls toward a black hole, it does not simply drop straight in. Conservation of angular momentum forces it into a spiraling orbit, forming a flattened accretion disk that rotates at tremendous speeds. Friction between adjacent layers of the disk heats the material to millions of degrees, and this thermal energy is radiated outward as electromagnetic radiation across the entire spectrum. The efficiency of this process can reach roughly 40% for a rapidly spinning black hole, meaning that 40% of the rest mass energy of the infalling matter is converted into light. Nuclear fusion, the process that powers stars, converts a mere 0.7%. Black hole accretion is nearly 60 times more efficient. If you could feed a black hole a single kilogram of matter, it would release energy equivalent to roughly 4.5 billion joules, enough to power the entire United States for a few hours. The universe stumbled upon the most efficient engine possible, and it installed it at the centre of nearly every large galaxy. During the quasar epoch, which peaked roughly 10 to 12 billion years ago, when the universe was only about 2 to 4 billion years old, these engines were running at full throttle. Gas was abundant, galaxy mergers were frequent, funneling vast quantities of fresh fuel towards central black holes. The result was a population of quasars so luminous that they can be detected across the entire observable universe. The most distant quasar currently known existed when the universe was only about 670 million years old, a blink after the Big Bang in cosmic terms, and it was already powered by a black hole of over 1 billion solar masses. How a black hole could grow so large so quickly remains one of the most pressing mysteries in astrophysics, connecting directly to the intermediate mass black hole problem we discussed earlier. The seeds had to be massive, the feeding had to be rapid, and the conditions had to be just right. Scholars still argue about which combination of factors dominated, and the debate shows no signs of resolution anytime soon. Here is a historical fact that illustrates how dramatically quasars reshaped our understanding of the cosmos. Before their discovery, most astronomers assumed the universe was relatively calm and uniform, a stately collection of galaxies drifting apart in the aftermath of the Big Bang. Quasars shattered that assumption. Their existence at enormous distances meant that the universe was far more energetic in its youth than anyone had expected, and their absence in the nearby universe meant that conditions had changed dramatically over cosmic time. Quasars became one of the strongest pieces of evidence against the steady-state theory, the idea that the universe looks the same at all times and places, which was the main rival to the Big Bang model in the mid-20th century. If the universe were truly in a steady state, quasars should be evenly distributed across all distances. They are not. They are concentrated in the distant, ancient universe, which means the cosmos has evolved, changed, aged. The Big Bang model predicted exactly this kind of evolution. The steady-state model could not accommodate it. Quasars helped kill an entire cosmological theory, which is quite an accomplishment for objects that most people have never heard of. The influence of quasars extends far beyond their own galaxies. The intense ultraviolet radiation pouring out of a quasar can ionize hydrogen gas across millions of light years, creating vast bubbles of hot, transparent intergalactic medium in a process called cosmic reionization. In the very early universe, before the first stars and quasars ignited, the intergalactic medium was a cold, neutral fog of hydrogen that was opaque to ultraviolet light. The first luminous sources punched holes in this fog, and over hundreds of millions of years, those holes expanded and merged until the entire intergalactic medium was ionized and transparent. Quasars are believed to have played a significant role in this process, particularly in its later stages, and studying distant quasars through the absorption patterns they imprint on background light has become one of the primary ways astronomers probe the conditions of the early universe. Each quasar spectrum is a core sample drilled through billions of light-years of intergalactic history. Here is a quirky detail that brings the quasar story back down to a human scale. In the 1980s, gravitational lensing by foreground galaxies was found to produce multiple images of distant quasars, splitting a single quasar into 2, 4, or even more ghost images arranged in symmetric patterns around the lensing galaxy. One famous example, called the Einstein cross, shows a single quasar lensed into 4 images arranged in a neat cross pattern around a foreground galaxy. The light in each image has taken a slightly different path through the gravitational field, which means the images show the quasar at slightly different times. If the quasar brightens or dims, the change appears in each image at a different moment, and by measuring the time delay between images, astronomers can calculate the distances involved and even estimate the expansion rate of the universe. A single quasar, lensed by a single galaxy, becomes a cosmological measuring tool. The universe is economical with its instruments. You watch the quasar light ripple across the void, illuminating clouds of intergalactic gas like a searchlight sweeping across fog, and you marvel at the sheer reach of these objects. A single black hole feeding at the center of a galaxy can influence the chemistry and temperature of gas millions of light years away. It can regulate star formation in its host galaxy through feedback. It can ionize the intergalactic medium and contribute to the transparency of the universe itself. Black holes are not just destroyers, they're architects, sculpting the large-scale structure of the cosmos through the energy they release. And sometimes, when the geometry is just right, they aim that energy directly at you, not metaphorically, literally. A beam of relativistic particles pointed straight at Earth, arriving at your doorstep with a frequency and intensity that has given astronomers genuine pause. These objects are called blazars, and one in particular has earned a reputation for keeping researchers up past their bedtimes. Imagine a quasar. You have a good picture of one by now, the blazing accretion disk. the superheated gas spiralling inward, the tremendous luminosity that outshines entire galaxies. Now imagine that this quasar has a jet, a narrow beam of relativistic plasma launched from the poles of the accretion disk at nearly the speed of light, just like the ones we saw in GRS 1915 plus 105, but scaled up to galactic proportions. Most of the time these jets point away from Earth at some comfortable angle, and we observe them from the side, like watching a fire hose spray from across the street. But every now and then, the cosmic geometry conspires to aim one of those jets almost directly at us. When that happens, you're no longer looking at a quasar. You're looking down the barrel of a blazar, and the view is extraordinary. The word blazar is a combination of Biel Lacertae, the prototype of one subclass of these objects, and quasar, and it was coined in the 1978 Pittsburgh Conference on Biel-Lac objects. The naming convention in astrophysics has never been accused of elegance, but the objects themselves more than compensate. A blazar appears far brighter than a typical quasar of the same intrinsic power, because relativistic beaming amplifies the jet's emission enormously when it points toward the observer. The effect is similar to the superluminal illusion we discussed with GRS 1915 plus 105, but here the consequences are more dramatic. The jet's radiation is Doppler boosted by factors of hundreds or thousands, making the blazar appear orders of magnitude more luminous than it would if viewed from the side. It is the same object, the same black hole, the same accretion disk, but the viewing angle transforms it from a distant curiosity into a cosmic searchlight shining directly into your eyes. Blazars emit across the entire electromagnetic spectrum, from radio waves through optical and ultraviolet to X-rays and gamma rays. The highest energy photons they produce are gamma rays, the most energetic form of light in the universe, with individual photon energies billions of times greater than visible light. These gamma rays are produced by electrons in the jet that have been accelerated to nearly the speed of light and are interacting with magnetic fields and ambient photon fields through processes called synchrotron radiation and inverse Compton scattering. The details are complicated enough to fill entire textbooks, and they have, but the takeaway is simple. A blazar is a particle accelerator the size of a solar system, powered by a black hole aimed at your planet, producing radiation energetic enough to be detected by satellites orbiting Earth. That is the kind of sentence that makes you want to check whether your homeowner's insurance covers acts of astrophysics. The blazar that has given astronomers the most persistent case of fascinated anxiety is Markarian 421, located roughly 400 million light-years from Earth in the constellation Ursa Major. That distance makes it one of the closest blazars to our solar system, which is both scientifically convenient and mildly unsettling. Markarian 421 was one of the first extragalactic sources detected at very high-energy gamma rays, observed by the Whipple Observatory's Gamma Ray Telescope in 1992, using a technique called imaging atmospheric Cherenkov detection. When an ultra-high-energy gamma ray strikes Earth's atmosphere, it triggers a cascade of secondary particles that travel faster than the speed of light in air, producing a faint flash of blue Cherenkov radiation that ground-based telescopes can detect. The Whipple Observatory caught these flashes coming from the direction of Markarian 421 and confirmed that the blazar was producing gamma rays with energies exceeding 300 billion electron volts. For context, the Large Hadron Collider, the most powerful particle accelerator built by humans, operates at energies of a few trillion electron volts. Markarian 421 achieves comparable energies using nothing but gravity, magnetic fields, and the reckless physics of a relativistic jet. What makes Markarian 421 particularly noteworthy is its variability. The blazar does not emit steadily. it flares, sometimes dramatically, brightening by factors of 10 or more over timescales of hours to days. During major flares, Markarian 421 becomes the brightest object in the gamma-ray sky, outshining everything else above the atmosphere. These flares are thought to be caused by shock waves propagating through the jet, regions where the magnetic field configuration changes abruptly and particles are accelerated to even higher energies. The rapid variability tells astronomers that the emitting region is compact, confined to a tiny volume within the jet, and the physics governing the flares is still not fully understood. Some models invoke magnetic reconnection, a process in which magnetic field lines snap and rearrange, releasing enormous amounts of energy in the process. Others propose turbulent cells within the jet that compress and accelerate particles stochastically. Scholars still argue about which mechanism dominates, and the debate has been enriched by multi-wavelength monitoring campaigns that observe Markarian 421 simultaneously across radio, optical, X-ray, and gamma-ray frequencies, building a comprehensive portrait of the flaring process. Here is a historical fact that connects blazars to a broader discovery. In 2017, the IceCube Neutrino Observatory at the South Pole, a cubic kilometre of Antarctic ice instrumented with thousands of photon detectors, recorded a single high-energy neutrino arriving from the direction of a blazar called TXS 0506 plus 056. Neutrinos are ghostly particles that interact so weakly with matter that trillions of them pass through your body every second without touching a single atom. Detecting one from a specific astrophysical source was a landmark achievement, and the coincident observation of a gamma-ray flare from the same blazar by the Fermi Space Telescope provided strong evidence that blazars are sources of high-energy cosmic neutrinos. This was the dawn of multi-messenger astrophysics applied to blazars, combining electromagnetic radiation with neutrino detections to build a more complete picture of the physics occurring inside relativistic jets. The implications are profound because neutrinos, unlike photons, are not absorbed or deflected during their journey and carry direct information about the conditions at their source. Here is a quirky detail that rarely appears in headline coverage. Blazars occasionally appear to turn off entirely, fading to a fraction of their usual brightness for weeks or months before reigniting. These quiescent periods are not well understood, but one hypothesis is that the jet temporarily changes direction, swinging slightly away from Earth's line of sight due to precession of the accretion disk or interactions with a second supermassive black hole in a binary system. If that is correct, then some blazars might be taking turns, periodically pointing their jets at us and then sweeping them away, like a lighthouse beam that only catches your eye on each rotation. The idea that a blazar might be part of a binary black hole system is tantalizing, because it connects the blazar phenomenon to the gravitational wave universe. If two supermassive black holes are orbiting each other closely enough to cause jet precession, they're also producing gravitational waves that future observatories might detect. The blazar would become not just a light source, but a gravitational wave source, a dual messenger from a single cataclysmic system. You pull back from Markarian 421's line of fire, grateful that 400 million light-years provides a reasonable buffer, and you consider the broader picture. Blazars are quasars caught at a specific dramatic angle, and they represent a small but spectacular fraction of the active galactic nuclei scattered across the universe. The jet that makes a blazar so terrifying is the same jet that provides feedback to its host galaxy, regulating star formation and shaping galactic evolution. Destruction and creation, again woven together by gravity and geometry. And now the geometry is about to change once more, because the next terror on your itinerary involves not one supermassive black hole but two, locked in a gravitational embrace so tight that they are spiraling toward each other with an inevitability that nothing in the universe can prevent. The collision, when it comes, will shake the fabric of space-time itself. Two giants circling each other in the dark. That is the scene unfolding ahead of you now, and the scale of it makes everything you have witnessed so far feel like a warm-up act. You are approaching a galaxy that has not one but two supermassive black holes at its centre, separated by a distance that is shrinking with every orbit, locked in a gravitational death spiral that has been tightening for hundreds of millions of years, and will end in one of the most cataclysmic events the universe is capable of producing. This is a binary black hole system, and the merger that awaits it will release more energy in a fraction of a second than all the stars in the observable universe emit in the same interval. That sentence is not hyperbole, it is math. The existence of binary supermassive black holes is a natural consequence of the way galaxies grow. Galaxies merge. This is one of the fundamental processes driving the evolution of large-scale structure in the cosmos. When two galaxies collide, their stars mostly pass through each other like two swarms of bees occupying the same space, because the distances between individual stars are so vast that physical collisions between them are vanishingly rare. But the supermassive black holes at the centres of the merging galaxies do not pass through each other. They sink toward the centre of the merged system through a process called dynamical friction, losing energy to interactions with surrounding stars and gas, and eventually they find each other. What follows is a long, intricate gravitational courtship that proceeds through several distinct phases, each governed by different physics, and each bringing the black holes closer together. In the first phase, dynamical friction dominates. The black holes, still separated by thousands of light years, interact gravitationally with the stellar population of the merged galaxy. Stars that pass close to a black hole are flung away at high velocities, carrying energy and angular momentum with them, and this loss of energy causes the black hole's orbit to decay. The process is slow, taking hundreds of millions of years, but it is relentless. Gradually, the two black holes sink toward the centre of the galaxy, and toward each other, like two marbles settling to the bottom of a bowl. When they are separated by roughly a parsec, about 3.26 light years, the process changes. At this scale, most of the stars that could interact with the binary have already been ejected, creating a depleted region called a loss cone, and dynamical friction becomes inefficient. This is the so-called final parsec problem, one of the most debated issues in gravitational dynamics. Theorists have argued for decades about whether binary supermassive black holes can actually cross this last parsec gap, or whether they stall indefinitely, orbiting each other at a fixed separation like two dancers who cannot quite close the distance. The resolution likely involves a combination of mechanisms, interactions with gas, triaxial galaxy shapes that continually refunnel stars into the loss cone, and possibly the influence of a third black hole from a subsequent galaxy merger. Scholars continue to argue about which mechanism is most important, and the answer may depend on the specific properties of each system. If the binary does cross the final parsec, gravitational wave emission takes over. At separations of roughly 1,000th of a parsec and below, the black holes are close enough that they lose energy efficiently through gravitational radiation. Ripples in space-time predicted by Einstein in 1916, and first directly detected by LIGO in 2015 from a stellar mass binary. The gravitational waves from a supermassive binary are far too low in frequency for LIGO to detect, oscillating over periods of months to years rather than milliseconds. But they fall squarely in the sensitivity band of pulsar timing arrays, which use the precise signals from millisecond pulsars distributed across the galaxy as a natural gravitational wave detector. In 2023, several pulsar timing array collaborations including Nanograv, the European Pulsar Timing Array and others, announced strong evidence for a gravitational wave background, a low hum of space-time vibrations permeating the universe, most likely produced by the combined signal of thousands of supermassive binary black holes spiraling toward merger across cosmic history. The detection was not of a single binary, but of the collective chorus, like hearing the roar of a distant ocean rather than a single wave, and it confirmed that supermassive binaries do cross the final parsec and do proceed toward merger. The merger itself, when it finally occurs, is beyond dramatic. In the last few orbits, the black holes are moving at a significant fraction of the speed of light, and they emit gravitational waves carrying energy equivalent to several % of their total combined mass, converted directly into ripples in space-time through Einstein's famous equivalence of mass and energy. For a pair of billion solar mass black holes, this means an energy release on the order of tens of millions of solar masses worth of pure gravitational radiation emitted in less than a second. The resulting gravitational wave pulse would be detectable across the entire observable universe by a sufficiently sensitive instrument. The Planned Laser Interferometer Space Antenna, LISA, a space-based gravitational wave observatory consisting of 3 spacecraft, flying in formation separated by millions of kilometers, is specifically designed to detect individual supermassive mergers when it launches, currently expected in the mid-2030s. LISA will open a window onto the gravitational wave universe at low frequencies that ground-based detectors cannot access, and supermassive binary mergers are among its primary targets. Here is a quirky detail that adds a dramatic flourish to the merger story. When 2 black holes of unequal mass merge, the gravitational waves are emitted asymmetrically, carrying more momentum in one direction than another. This imbalance delivers a recoil kick to the newly formed black hole, which can be launched out of the galactic center at speeds of hundreds or even thousands of kilometers per second. In extreme cases, simulations predict recoil velocities exceeding 4,000 kilometers per second, which is fast enough to escape the gravitational pull of any galaxy in the universe. The merged black hole would be ejected from its host, sent flying into intergalactic space as a wandering supermassive black hole, untethered and invisible. The thought of a billion solar mass black hole drifting through the voids between galaxies is extraordinary, and there is tentative observational evidence for recoiling black holes in a few systems where the central engine appears to be displaced from the galactic center. If these identifications are confirmed, they represent the aftermath of mergers so violent that not even the galaxy could hold on to the result. Here is a historical fact that places this entire field in context. The possibility that binary supermassive black holes exist was first proposed in the 1980s, not long after it became clear that most large galaxies harbour central black holes, and that galaxy mergers are common. But the observational evidence remained circumstantial for decades, limited to indirect signatures like double-peaked emission lines in active galactic nuclei, which could indicate 2 sets of gas orbiting 2 separate black holes, but could also be produced by other configurations. The first spatially resolved image of a binary supermassive black hole system, showing 2 distinct compact radio sources at the center of the galaxy 0402+379, was published in 2006, with the 2 black holes separated by about 24 light-years. That system is now one of the best study candidates, and monitoring its orbital evolution is a long-term project that will unfold over decades or centuries. The black holes in 0402+379 are close enough to be gravitationally bound but still far from merger, a snapshot of the slow middle act of a process that began with a galaxy collision and will end with a space-time earthquake. You watch the binary ahead of you, two invisible points of immense gravity circling their common centre of mass. Their accretion disks distorted and interacting, gas streaming between them in complex turbulent bridges. The system is beautiful in its inevitability. Nothing can stop the inspiral. Nothing can undo the gravitational radiation that is slowly, steadily draining energy from the orbit. One day, perhaps millions of years from now, the two will touch, and the universe will ring like a bell. But you will not be here for that. You're turning now toward the very beginning of time, because some of the strangest and most terrifying black holes are not the ones that formed from dying stars or growing galaxies. They are the ones that may have existed before either stars or galaxies were born, forged in the first fraction of a second after the Big Bang itself. You're falling backward through time now, not gently, not in the leisurely rewind of a nature documentary, but in a headlong rush toward the origin of everything. Stars unform, galaxies dissolve into clouds of hydrogen and helium. The cosmic microwave background, that faint afterglow of the Big Bang that permeates all of space, brightens and tightens around you like a warming blanket. The universe shrinks, heats, compresses, and you are hurtling toward a moment so early and so extreme that the laws of physics as you understand them begin to blur at the edges. You are heading for the first fraction of a second after the Big Bang, a sliver of time so thin that writing it as a decimal would require more zeros than this script has words. And in that sliver, according to a theory that has been gaining quiet momentum for decades, black holes may have been born. Not from stars, because stars did not yet exist. Not from collapsing gas clouds, because gas had not yet cooled enough to collapse. These black holes would have been forged directly from the raw density fluctuations of the infant universe itself, and they are called primordial black holes. The idea was first proposed in the early 1970s by Stephen Hawking and Bernard Carr, building on earlier suggestions by Yakov Zeldovich and Igor Novikov in the Soviet Union. The reasoning was elegant in its simplicity. In the very early universe, matter and energy were distributed almost but not perfectly uniformly. Tiny fluctuations in density, quantum ripples amplified by the rapid expansion of space during inflation, created regions that were slightly denser than their surroundings. In most cases, these overdensities were small and eventually grew into the large-scale structures we see today, galaxies, clusters, filaments, through the slow pull of gravity over billions of years. But if a fluctuation were large enough, if a particular region of the early universe was sufficiently overdense, it would not need to wait for gravity to do its gradual work. It would collapse immediately within the first second of cosmic history, directly into a black hole. No star required, no supernova necessary, just density, gravity, and timing. The mass of a primordial black hole would depend on when during the early universe it formed. The earlier the formation, the smaller the mass, because the cosmological horizon, the region causally connected at any given moment, was smaller at earlier times. A primordial black hole forming at roughly 1 microsecond after the Big Bang would have a mass comparable to our Sun. One forming at a nanosecond would be much lighter, perhaps comparable to a mountain. And one forming at the Planck time, the smallest meaningful unit of time in physics, would have a mass of roughly 20 micrograms, the mass of a grain of sand. These microscopic primordial black holes are particularly fascinating because, as we will explore in the next section, Hawking radiation predicts that black holes of sufficiently small mass should evaporate over time, and a Planck mass black hole would have evaporated almost instantly. Slightly heavier ones might have survived for millions or billions of years before vanishing in a burst of radiation. The lightest primordial black holes that could still exist today would need an initial mass of roughly 1 billion kilograms, about the mass of a small asteroid, to have survived the full 13.8 billion years since the Big Bang. Anything lighter has already evaporated if Hawking's theory is correct. Here is the historical context that makes primordial black holes more than just a theoretical curiosity. For decades, cosmologists have been searching for the identity of dark matter, the mysterious substance that makes up roughly 27% of the universe's total energy content, but does not interact with light or ordinary matter in any detectable way. Its presence is inferred entirely from gravitational effects, the rotation curves of galaxies, the dynamics of galaxy clusters, the pattern of the cosmic microwave background, and the growth of large-scale structure. Dozens of candidates have been proposed, from exotic particles like WIMPs and axions to modifications of gravity itself, but none have been conclusively detected despite decades of increasingly sensitive experiments. In this context, primordial black holes have emerged as a dark horse candidate, if you'll pardon the expression. If primordial black holes formed in sufficient numbers and in the right mass range, they could account for some or all of the dark matter, gravitationally influencing the universe exactly as observations demand while remaining dark, compact, and essentially invisible. The idea has been tested against a wide range of observational constraints, and the results are tantalizing but inconclusive. Microlensing surveys have ruled out primordial black holes as the dominant form of dark matter across a broad range of masses, from roughly 1/1000th of a solar mass to tens of solar masses, because such objects would produce detectable lensing events when they pass in front of background stars, and the observed rate of such events is too low. However, there are windows in the mass spectrum, particularly around 100,000th of a solar mass, and in the range of tens to hundreds of solar masses. Where the constraints are weaker and primordial, black holes could still contribute significantly. The LIGO detections of unexpectedly heavy stellar mass black hole mergers, including the infamous GW190521 event, with its pair instability-defying masses, have fueled speculation that some of these merging objects might be primordial rather than stellar in origin. If two primordial black holes happened to form near each other in the early universe and remained gravitationally bound, they could spiral together and merge billions of years later, producing exactly the kind of gravitational wave signal LIGO has detected. The hypothesis is speculative, but it is testable, and distinguishing primordial mergers from stellar mergers is an active area of research. Here is a quirky detail that illustrates how creative the theoretical work in this field has become. Some researchers have proposed that primordial black holes could have served as seeds for the supermassive black holes we observe at the centres of galaxies, neatly solving the problem of how those monsters grew so large so quickly. If a primordial black hole of, say, 100,000 solar masses formed in the early universe, it would have a tremendous head start over a stellar mass seed, requiring far less accretion to reach the billion solar mass scales observed in high redshift quasars. This idea connects the smallest and the largest black holes in a single narrative thread, from quantum fluctuations in the first fraction of a second to the blazing quasars of the young universe, and it is precisely the kind of sweeping cross-scale connection that physicists find irresistible. Whether it is true is another matter entirely, and scholars continue to debate the viability of the primordial seeding scenario against alternative models involving direct collapse of massive gas clouds and rapid early accretion. There is something haunting about the idea of primordial black holes. They are relics, survivors from an epoch so alien that our physical intuitions are useless. The universe at 1 microsecond old was a seething plasma of quarks and gluons, far too hot for atoms or even protons to exist as stable entities. The density was trillions of times greater than the density of an atomic nucleus. And in that unimaginable environment, gravity may have pinched off pockets of space-time and sealed them away forever, creating objects that have been drifting silently through the cosmos ever since, older than every star. older than every galaxy, older than the cosmic microwave background itself. If one were to drift past you right now, you would never know. It would be invisible, lightless, perhaps the mass of a small moon, detectable only by the faintest gravitational tug on nearby objects. It would be a fossil from the birth of the universe, preserved in the amber of its own event horizon. You let the early universe fade behind you, its blinding heat cooling to the gentle hiss of background radiation, and you return to more familiar cosmic surroundings. But the story of primordial black holes has opened a door to an even stranger idea, one proposed by the same Stephen Hawking who helped birth the primordial hypothesis in the first place. It is the idea that black holes are not entirely black, that they slowly, inexorably leak, and that given enough time they can vanish entirely in a final cataclysmic flash. It is called Hawking radiation, and it is one of the most beautiful and disturbing predictions in all of theoretical physics. Stephen Hawking was 32 years old when he broke black holes, not literally of course, but theoretically, which in physics is arguably more disruptive. The year was 1974, and Hawking, already renowned for his work on singularity theorems and the mathematical foundations of black hole mechanics, published a paper that stunned the theoretical physics community. The paper demonstrated, through a careful application of quantum field theory to the curved space-time around a black hole, that black holes are not perfectly black. They emit radiation. Slowly, faintly, but inexorably, a black hole radiates particles into space, losing mass in the process, and if nothing replenishes that mass, the black hole will eventually evaporate entirely and disappear. The prediction was called Hawking radiation, and it married quantum mechanics to general relativity in a way that nobody had anticipated, and that half a century later, nobody has fully reconciled. The mechanism is rooted in the quantum vacuum, which is not as empty as its name suggests. In quantum field theory, even the most perfect vacuum is a seething froth of virtual particle pairs, matter and antimatter partners that pop into existence, borrow energy from the uncertainty principle, and annihilate each other almost instantly, returning the borrowed energy before the universe notices the debt. This process happens everywhere, all the time, and under normal circumstances it has no observable consequences beyond subtle effects like the Casimir force and the Lamb shift. But near the event horizon of a black hole, something extraordinary happens. A virtual pair can form in such a way that one partner falls across the event horizon while the other escapes into space. The escaping particle becomes real, carrying positive energy away from the black hole, while the captured partner, from a certain theoretical perspective, carries negative energy into the black hole, reducing its total mass. The net effect is that the black hole emits a steady stream of particles and loses mass over time. It is as if the event horizon is slowly dissolving, leaking its contents back into the universe one quantum at a time. The temperature of Hawking radiation is inversely proportional to the black hole's mass, which leads to a deeply counterintuitive result. A large black hole is cold. A supermassive black hole like Escarres star, with 4 million solar masses, has a Hawking temperature of roughly 14 billionths of a billionth of a degree above absolute zero. That is unimaginably cold, far below the current temperature of the cosmic microwave background, which means Escarres star actually absorbs more energy from its environment than it emits through Hawking radiation. It is gaining mass from the background radiation of the universe faster than it is losing mass through quantum evaporation. For any astrophysical black hole, stellar or supermassive, Hawking radiation is completely negligible, overwhelmed by even the faintest trickle of accretion. You would never detect it, and it would never matter on any timescale shorter than the absurd. But small black holes are a different story. a black hole with a mass of roughly 1 billion kilograms, about the mass of a small mountain, would have a temperature of over 100 billion degrees, hotter than the center of the most massive stars, and it would radiate fiercely. As it loses mass, it gets hotter, and as it gets hotter, it radiates faster, creating a runaway feedback loop that accelerates as the black hole shrinks. The final moments of an evaporating black hole are genuinely apocalyptic. In the last tenth of a second, the remaining mass is converted into a burst of radiation and particles with an energy equivalent to roughly 1 million megaton nuclear explosions, a flash brighter than 1 billion nuclear detonations compressed into an instant shorter than a heartbeat. If any of those primordial black holes we discussed earlier had an initial mass just below the survival threshold, they would be reaching the end of their evaporation process right about now, and their death throes would be detectable as brief, intense bursts of gamma rays. Astronomers have searched for such bursts, and so far none have been convincingly identified, which places limits on the abundance of small primordial black holes, but does not rule out their existence entirely. Scholars still debate the observational signatures and whether existing gamma-ray data might contain unrecognized evaporation events buried in the noise. Here is a historical fact that underscores how revolutionary Hawking's prediction was. Before 1974, the established understanding of black holes was summarized by the no-hair theorem, which states that a black hole is completely described by only 3 properties: mass, charge, and angular momentum. Everything else about the matter that formed it, its chemical composition, its shape, its history, is irretrievably lost behind the event horizon. Jacob Bekenstein, a graduate student at Princeton, had proposed in 1972 that black holes should have entropy, a measure of disorder proportional to the area of the event horizon, because without entropy, a black hole would violate the second law of thermodynamics. You could decrease the total entropy of the universe simply by throwing high-entropy matter into a black hole, which seemed wrong. But entropy implies temperature, and temperature implies radiation, and nobody took the implications seriously until Hawking demonstrated it with rigorous mathematics. Bekenstein was right about the entropy. Hawking showed that the temperature was real and the radiation was inevitable. Together they established that black holes are thermodynamic objects, subject to the same laws of thermodynamics that govern everything from steam engines to stars. Here is a quirky detail that makes the story even richer. Hawking initially resisted Bekenstein's entropy proposal, arguing that it could not be correct because a black hole with a temperature would have to radiate, and everyone knew black holes did not radiate. Then Hawking sat down and did the calculation properly, discovered that black holes do radiate, and effectively proved Bekenstein right in the process of trying to prove him wrong. It is one of the most charming intellectual reversals in the history of physics, a moment where stubbornness led directly to a breakthrough, and Hawking was characteristically gracious about it in later years, readily crediting Bekenstein's insight as the essential precursor to his own discovery. Hawking radiation has never been directly observed, and it may never be, at least not from an astrophysical black hole. The temperatures involved for stellar and supermassive black holes are so fantastically low that the radiation is lost beneath every conceivable noise floor. However, laboratory analogues of Hawking radiation have been created using sonic horizons in superfluid helium and Bose-Einstein condensates, systems where sound waves play the role of light and flow boundaries mimic event horizons. These analog experiments have detected thermal radiation consistent with Hawking's predictions, providing indirect but compelling support for the underlying physics. The experiments do not prove that astrophysical black holes radiate, strictly speaking, because the analogy is not perfect, but they demonstrate that the mathematical framework Hawking used produces correct predictions in systems where it can be tested. For most physicists, this is sufficient grounds to take Hawking radiation very seriously, even in the absence of direct astronomical evidence. You watch an imaginary tiny black hole flicker in the void ahead of you, its event horizon no larger than an atom, its temperature blazing at trillions of degrees, radiating a furious spray of particles and photons as it consumes itself in a feedback loop of shrinking mass and rising temperature. It is a dying ember of space-time burning brighter as it grows smaller, racing toward a final instant of annihilation that will leave behind nothing but a fading wash of radiation and a profound question. What happened to all the information that fell in? The matter, the energy, the quantum states of every particle that crossed the event horizon over the black hole's lifetime. Where did it go? This question, innocent on its surface, has ignited the fiercest debate in theoretical physics for the past 50 years, and it remains unsolved. You're about to wade into it, and the water is deep. The question sounds simple enough to fit on a napkin. If a black hole evaporates completely through Hawking radiation, what happens to the information about everything that fell into it? You toss a book into a black hole. The book had words, pages, a specific arrangement of atoms encoding a specific story. The black hole swallows it, grows infinitesimally heavier, and then, over eons, evaporates into a featureless haze of thermal radiation. That radiation, according to Hawking's original calculation, is perfectly random, perfectly thermal, carrying no imprint of the book whatsoever. The words are gone. The story is gone. The specific quantum state of every atom in every page has been erased from the universe, not just scrambled or hidden, but genuinely destroyed. And that, according to quantum mechanics, is not allowed. This is the black hole information paradox, and it has been tormenting theoretical physicists since Hawking first articulated it in the mid-1970s. General relativity says that what falls past the event horizon is gone forever, sealed behind a one-way membrane from which nothing returns. Quantum mechanics says that information is never destroyed, that the laws governing quantum states are unitary, meaning they can always be run backward in principle. Every quantum process is reversible. Every final state contains the complete history of how it was produced. If you had perfect knowledge of the Hawking radiation emitted by an evaporating black hole, you should be able to reconstruct everything that ever fell in. But Hawking's calculation says the radiation is thermal, random, information-free. The two pillars of modern physics are giving contradictory answers, and at least one of them must be incomplete. Hawking initially sided with general relativity. In 1981, at a conference in San Francisco, he argued that black holes do destroy information, and that physicists would simply have to accept this as a new and uncomfortable feature of nature. The reaction from the quantum mechanics community was immediate and sharp. Leonard Susskind and Gerard 't Hooft fired back, insisting that information destruction was so fundamentally incompatible with quantum mechanics that any theory predicting it must be flawed. Susskind later described the ensuing decades-long debate as a war, fought with equations rather than weapons, but pursued with genuine intellectual ferocity. If Hawking was right, quantum mechanics needed modification at its deepest level. If Susskind was right, general relativity's description of black holes was missing something critical. Either way, one of the foundations of physics was cracked. The first major resolution attempt came through the holographic principle, developed by 't Hooft and Susskind through the 1990s. The idea proposes that all information about a black hole's interior is encoded on its event horizon, spread across the two-dimensional surface like data on a hard drive. The three-dimensional interior is, in some deep sense, a projection of this boundary, a hologram. Information never truly enters the interior. It is smeared across the horizon, and eventually re-emitted in Hawking radiation, scrambled beyond recognition but not destroyed. This received powerful support from Juan Maldaceno's 1997 result, demonstrating a mathematical equivalence between a gravity theory in curved spacetime and a quantum theory without gravity on its boundary. This correspondence, called ADS/CFT duality, provided a framework where information is preserved during evaporation, at least in the idealized spacetime Maldaceno studied. Whether it extends to our actual universe remains vigorously debated. Then came the firewall. In 2012, physicists Almheri, Marolf, Polchinski and Sully, often abbreviated as AMPS, published a paper showing that three widely held beliefs could not all be true simultaneously: that Hawking radiation carries information, that an observer notices nothing special crossing the event horizon, and that physics remains consistent outside the black hole. If information is encoded in the radiation, then an infalling observer would not experience a smooth crossing. Instead, they would encounter a blazing wall of high-energy particles at the horizon, a firewall that would incinerate anything attempting to cross. The event horizon, long described as an invisible boundary you would sail through without noticing, would become a lethal barrier of screaming radiation. The firewall contradicted the equivalence principle of general relativity, which insists that free-falling observers should not detect gravitational fields through local experiments. Crossing a sufficiently large black hole's horizon should feel like crossing empty space. A firewall would make the horizon a detectable, violent location, violating one of Einstein's foundational principles. Some physicists accepted this as the price of preserving quantum unitarity. Others argued the firewall was an artifact of flawed assumptions. Hawking weighed in with a provocative 2014 proposal, suggesting event horizons might not exist traditionally at all, replaced by what he called apparent horizons, temporary boundaries that shift and dissolve, allowing information to eventually leak out. The proposal was characteristically bold and characteristically vague on mathematical details, satisfying almost nobody while inspiring fresh exploration. Here is a quirky detail illustrating the depth of confusion. In 2017, Susskind proposed connecting the paradox to quantum computational complexity, arguing that a black hole's interior functions as a quantum computer, performing increasingly complex operations on infalling information. The information is not destroyed but becomes so scrambled that extracting it requires solving a computational problem of almost inconceivable difficulty. The black hole grows not in spatial volume but in computational complexity, a concept Susskind called complexity equals volume. The proposal blends quantum information theory, computer science, and general relativity in ways unimaginable a generation ago, suggesting the resolution may require new mathematics from entirely unexpected fields. Scholars still argue about all of this. The information paradox remains officially unsolved. The holographic principle works in Maldaceno's idealized spacetime, but remains unproven for our universe. The firewall preserves unitarity but violates the equivalence principle. Hawking's apparent horizons lack rigorous mathematics. Susskind's complexity approach is elegant but untested. The only consensus is that the paradox reveals something profound about spacetime, gravity and quantum mechanics, something requiring a full theory of quantum gravity to resolve. That theory does not yet exist, though string theory, loop quantum gravity, and other approaches compete for the honour. You drift in the silence, surrounded by the ghost of an evaporated black hole, and you feel the weight of the unsolved pressing against your thoughts. Physics has reached a boundary here, an event horizon of understanding beyond which current theories cannot see. The universe keeps its deepest secrets behind horizons, and the only way forward is to build better tools, ask sharper questions, and remain comfortable with uncertainty. You're good at that by now. You have been practicing all night, and now, with the paradox still humming softly in the background, it is time to look ahead, far ahead, to the end of everything, where black holes play their final, solitary role in a universe gone dark and cold. You fast forward now, not by millions of years or even billions, but by numbers so large they require their own notation to write down. You are skipping past the era when stars still burn, past the era when white dwarfs cool and fade, past the era when galaxies dissolve into scattered remnants drifting apart in an ever-expanding void. You are heading for the deep future, the unimaginably remote epochs when the universe has exhausted every conventional source of energy and light, and the only objects still persisting in the endless dark are black holes. They are the last survivors, the final inheritors of a cosmos that has run out of everything else, and their vigil will last longer than anything that came before by a margin so absurd that the entire current age of the universe, all 13.8 billion years of it, becomes a rounding error. This is the black hole era, and it is where our journey ends. The timeline of the far future is typically described using powers of 10, because ordinary numbers simply cannot keep up. The current age of the universe is roughly 10 to the power of 10 years. The last conventional stars, the tiny miserly red dwarfs that hoard their hydrogen fuel with extraordinary efficiency, will burn out in roughly 10 to the power of 13 or 14 years, about 1,000 times the current age of the cosmos. After that, the stellar era is over. No new stars will form because the raw materials, the vast clouds of molecular hydrogen that served as stellar nurseries, will have been used up or dispersed beyond recovery. The universe will go dark in the conventional sense, lit only by the fading glow of cooling stellar remnants, white dwarfs becoming black dwarfs, neutron stars losing their heat to the vacuum, and the occasional flicker of energy released when objects collide or decay. But the black holes will remain. Stellar mass black holes, supermassive black holes, and whatever intermediate mass specimens have accumulated over cosmic history will persist because, in the absence of significant Hawking radiation, they're essentially immortal. They do not cool, they do not decay through any known force. They simply sit, warping space-time around themselves, occasionally capturing a stray particle or photon that wanders too close. Over timescales that dwarf the stellar era, these black holes will grow slightly by absorbing the cosmic microwave background radiation, which itself will have cooled to temperatures inconceivably close to absolute zero. The universe during this period is a vast, dark, nearly empty expanse, dotted with invisible gravitational wells, each one a memorial to the stars, galaxies, and quasars that once blazed with furious energy. Here is a historical fact that frames this future in the context of scientific thought. The concept of the heat death of the universe was first articulated in the 19th century by Lord Kelvin and Hermann von Helmholtz, building on the second law of thermodynamics, which states that entropy in a closed system always increases. They realised that if the universe is a closed system, it must eventually reach a state of maximum entropy, a condition in which no energy gradients remain and no further work can be done. Everything reaches the same temperature. All processes stop. The universe does not explode or collapse. It simply winds down, like a clock with no one to rewind it. The idea was deeply unsettling to Victorian sensibilities, and it remains unsettling today, though modern cosmology has added layers of nuance that Kelvin could not have anticipated. Hawking radiation is the mechanism by which even the black holes eventually surrender. Remember that the temperature of Hawking radiation is inversely proportional to mass. During the black hole era, the cosmic background temperature will eventually drop below the Hawking temperature of even the most massive black holes, and at that point the black holes will begin to lose mass faster than they gain it. The process is fantastically slow. A stellar mass black hole of 10 solar masses would take roughly 10 to the power of 67 years to evaporate. A supermassive black hole like a grey star at 4 million solar masses would last roughly 10 to the power of 87 years. And the most massive black holes, the 100 billion solar mass titans like Phoenix A, would endure for something approaching 10 to the power of 100 years, a googol of years, a number so large that writing it out would require more digits than there are atoms in the observable universe. But even a googol of years is not eternity. Eventually every black hole will evaporate. The final moments of each one will replay the same script we described when discussing Hawking radiation, the runaway heating, the accelerating radiation, the final burst of particles and light as the last scrap of mass is converted into energy and flung outward. Each evaporating black hole will briefly illuminate its corner of the dead universe like a flashbulb going off in an abandoned warehouse. A tiny, furious flare of existence in an ocean of nothing. And then it will be gone, and the darkness will close back in, a little more complete than before. Here is a quirky thought that some physicists have entertained with varying degrees of seriousness. The final evaporation of the last black hole in the universe might be the last interesting event that ever occurs. After that, the cosmos enters what is sometimes called the Dark Era, an eternity of expansion and silence in which nothing happens, nothing changes, and nothing exists in any organized form. Protons may have decayed by then, if proton decay is real, reducing all remaining matter to a thin soup of electrons, positrons, neutrinos, and photons spread across a volume so vast that no two particles will ever interact again. Scholars debate whether this is truly the final state, or whether quantum fluctuations over incomprehensible timescales might spark new structures, new phases, perhaps even new universes bubbling out of the vacuum. The answer lies so far beyond our current ability to test that it belongs more to philosophy than physics, but it is a question worth carrying gently into sleep. You have travelled from the birth of black holes to their death, from stellar corpses to ultramassive titans, from the first fraction of a second after the Big Bang to the last evaporating remnant in a universe gone cold. You have stood at event horizons and peered into paradoxes. You have watched stars die, jets ignite, and space-time bend into shapes that language can barely contain. The darkness you have been exploring all night is not empty. It is full of structure, full of mystery, full of questions that the brightest minds in history are still working to answer. That, more than anything, is what makes black holes not just terrifying, but beautiful. They are the places where understanding breaks down, and breaking down is how understanding grows. So let your breathing slow now. Let the numbers fade, the way starlight fades when morning begins to creep across the sky. Let the event horizons and singularities and paradoxes dissolve into the soft hum of whatever room you're lying in, the gentle whir of a fan, the quiet creak of a house settling into night, the distant murmur of a world that is still turning, slowly, reliably, held in its orbit by the same gravity that built everything you learned about tonight. The universe is vast and strange and occasionally terrifying, but you're here, warm, safe, wrapped in gravity just strong enough to keep you gently pressed against your mattress and not a fraction stronger. The stars outside your window are burning steadily, billions of years from fading. The nearest black hole is comfortably, wonderfully far away. There's nothing to solve right now, nothing to calculate, nothing to fear. The cosmos has kept its vigil for 13.8 billion years without your help, and it will keep it for a little while longer while you rest. Tomorrow, when you wake, the universe will still be there, patient and magnificent, waiting for you to wonder about it again. The questions will still be open. The mysteries will still be glowing faintly at the edges of human knowledge, inviting you back whenever you are ready. But that is tomorrow. Right now there is only this breath, and the next one, and the soft, heavy warmth of sleep settling over you like a blanket made of stardust. Close your eyes. Let the dark be soft. Let it be kind. You have earned this quiet. The abyss has looked back at you all night, and you did not blink. Sweet dreams.